Hi, everyone, and welcome to the third and last hour of the lectures about function secret sharing. Now, people complained about the resolution of the huge video stream we had on Zoom. So in parallel, we opened a broadcast on YouTube. I posted on the chat channel and on Slack links to a YouTube page with broadcast the lecture live, and it has much better resolution. So you are all urged to move to the YouTube page and keep posting your questions on Slack. And now let's go to Alette and to the last hour.
Hi, thanks, Benny. Yes, I swear my slides aren't pixelated on their own, nor am I. Before I pick back up for the final section here today, two questions that popped up, although now I'm not sure I remember what they were. So one of them was asking about the communication size, or rather the share size of the FSS for point functions of the DPF construction. I don't know is the answer. I don't know if we can do better. So right now, and I'll talk about this a little bit at the very, very end, but right now we basically have something like lambda times n, and you could hope to get possibly down as low as lambda plus n, which actually in practice makes it quite a big difference. I don't know, and I have secret inputs here, x and y, and they want to talk to each other back and forth somehow to learn some function f evaluated on x and y, but nothing else about x or y. Okay. So this is a beautiful line of work. It's actually one of the main things that I work on in addition to function secret sharing and beyond. And over the last decade, so since the 80s, where it was shown that you can do this for any function based on certain computational assumptions, there's been a ton of work of trying to get more efficient solutions. And one of the nice observations here, dating back to Beaver in 91, is that you can consider a version with pre-processing, okay, where there's like this offline phase that results in Alice and Bob getting some sort of correlated randomness. But this part is independent of the inputs, okay? So this you can think about running long overnight or whatever. Then when the inputs actually come along, in the online phase, the communication in some of these constructions can be very cheap and more succinct. So this is a nice feature where it sort of pushes work into a pre-processing phase where costs are more acceptable. Okay, and in such a setting, there's two obvious and semi-orthogonal questions. One is, what types of correlations are useful? How can you kind of use this correlated randomness? And there's been bits and pieces of different observations kind of, or like works, showing that different types of correlated randomness can actually give you secure computation savings in the online period. So it dates back, of course, to Beaver, if you've heard of multiplication or Beaver triples. Tiny tables was a more recent work using something called one-time truth tables. There's some other odds and ends, but kind of sort of when I approach this literature, it's a little bit of like a little bit of disconnected tricks. It wasn't really clear what's going on there. Okay, but a second question, which I'm actually not going to talk about at all, is how to generate such correlations. Okay, so going back to the picture, in some sense, I've kind of pushed a lot of the work to the pre-processing, and it typically actually ends up being the case that the cost of generating this pre-processing, which also needs communication and needs computation, ends up being one of the bottlenecks of the cost, one of the more expensive parts of the protocol. Okay, so there's a lot of motivation of potentially trying to generate these correlations, for example, with low communication or low costs. I'm not going to touch on this, but let this be a shout out to the talks of Peter and Yuval about pseudorandom correlation generators on Wednesday and Thursday. And this is exactly addressing that question. Okay, so now I'm pushing that to the side, and let's go back to what types of correlations are useful here. Okay, and the basic framework of secure computation with preprocessing is that you start with the program of this function f that you want to compute, and you express it as some arithmetic circuit. Okay, So this kind of forces you to choose some ring, some arithmetic space that you're working over, and you've got these gates that are addition and multiplication over this ring. Again, for example, Beaver showed how can you take each of these kind of multiplication gates, or the expensive ones there, and for each multiplication gate, take a multiplication triple. This is going to be generated as part of the pre-processing that allows you to, in the online part, effectively and cheaply do secure computation of that given multiplication gate. Okay, so arithmetic circuits, these multiplication gates are one example. The general truth tables with tiny tables is kind of another example. And let me post kind of a more broad goal here. Suppose that you have a goofy looking circuit. Maybe you have different domains, not just, for example, ring elements. Maybe for part of it, you want ring elements to do multiplications over arithmetic space, but then you actually want the bit representations of these values, or you want to do something that's much more efficient of these values and so forth. And it can be very general here. And the goal for this part is asking, can we somehow come up with a way that's comparable to, for example, this Beaver multiplication triples that takes the cost of the multiplication gate and pushes it up? Can we do that for these more expressive or different types of gates? Okay, and the punchline here is yes, that function secret sharing actually gives you a tool for doing that. Okay, I'm not going to go into much detail because I want to talk about all sorts of other things. But the high-level framework is that if you start with a circuit of this form, and if you have function secret sharing schemes, okay, that support various classes that relate to the types of gates in your circuit. Okay, so for example, this is supposed to be like whatever this gate is here. This is going to be some function class related to this gate. I'll get to that. Then putting these two together, you can compile this into a 2PC protocol with pre-processing that allows you to kind of push the expensive cost of these now strange shaped gates up to the pre-processing. And this is cool, I think, for two different reasons. One, at a purely theoretical level, this approach actually unifies the list that I had on the previous slide of, for example, multiplication triples, of tiny tables, of some of these other constructions. All of those can actually be cast exactly as cases of this framework using FSS of different kinds. But even beyond that, of course, that this not only explains existing things, but this gives new solutions, new approaches that are very promising in terms of practical solutions for 2PC protocols with low online communication complexity. And the goal is to be able to support different types of gates, things like equality or comparison or bit decomposition, by leveraging the power of FSS schemes that we can build. As a brief aside, which I'm not going to get into deeper, you can certainly ask, is FSS necessary? Is this sort of an overkill? Or can you maybe hope to do things without it? We don't have a full answer to that, but something that we can say is that for a certain type of gate, calling it shared equality, sort of like an equality match, if you have optimal online communication, like we're going to be able to achieve in our transformation here, then this actually implies one-way functions, which in a sense does imply, for example, DPFs, which is the FSS that we use for that case. Okay, so the punchline here is that it does seem to be the case that possibly for getting really cheap communication complexity for certain types of gates here, in some sense, you do need cryptographic tools that are comparable to function secret sharing. Okay, so I've kind of hand waved at what are these FSS classes, or what are the function classes rather that are relevant here, and in a little bit more detail. So note that if I start with the circuit is public. Okay, in particular, I keep thinking I can click on this. Each of these gates is also public. Nobody's trying to hide any secrets here about what the gate is, for example. So you can ask, what is the function secret sharing going to be for? It's to take a secret function and to split it into parts. And what it's going to turn out being is that what the tool that we need will be function secret sharing for a class of functions that correspond to what I'm referring to as secret offset functions. Okay, so say, for example, this is some public gate G, then the corresponding function class we want FSS for will be the class of all the G of X minus R for secret values R. And I'm not going to get into, unfortunately, the details or even any sort of explanation of why is that the case. Let me just say one sentence maybe, which is that the transformation in this protocol will give a protocol where basically in the online period, for every single wire in the circuit, you'll exchange exactly one value that's going to be exactly the size of whatever the payload is on that wire. So for example, if this is some ring element here, we'll exchange a ring element. If these are bits here, then for each of those, we'll exchange one bit. Okay, and the idea is that what we'll exchange will give us shared up, so we can put those together, a masked value of whatever the real semantic value is that we've just evaluated on that wire. Okay, so for example, if you were evaluating this on our inputs in the clear and this was a 0, then what we'll end up getting is the value 0, but masked by some secret value R. Okay, and the function secret sharing is going to play the role that when we both have inputs, a masked input value, okay, something like an X minus R, we will use, or sorry, X plus R, okay, we will use our shares of this function, the corresponding function, which is the function that intuitively removes the mask, applies the gate, and it in effect kind of adds the next mask on. Okay, so this is very brief. I don't want to actually get much, okay, I really do want to get much deeper into this, but I shan't due to time. But I'm happy if anybody has questions afterward that I can go into further detail. Okay, but so the punchline that I want you to remember, at least for this part, is exactly that given a circuit with certain types of gates, that the FSS that you want is for the class of these offset functions. Okay, and we'll see many examples of that. Okay, so going back to, I want to basically instantiate this transformation, okay, plugging in different constructions of FSS that we know and that we have, okay? And let me start by going back to the very beginning of the first lecture, where I gave some simple examples of information theoretically secure FSS. Okay, so for example, if you recall, for any function class, you can always just take the truth table and secret share it. Okay, this was one construction that we had. I also showed these low degree polynomials. Okay, remember that you just secret share the coefficients. These, these alphas have nothing to do with the DPF alphas, but these are like the AIs, the secret coefficients of the polynomial. And even slightly more broadly, we saw with this observation that if I have any collection of public functions, okay, and secret linear coefficients, that I can also handle FSS of that function class. Okay, so these are 3 examples of FSS constructions. And now let us see, what do these already buy us? Okay, turns out, even the simple FSS of secret sharing the truth table, and remember, so what is the function class? I have some public gate, which is just some, now described as some big truth table, okay? And the function that we're actually splitting, that we're secret sharing, is that truth table, but where the input is offset by some secret mask, okay? Just think about it as sort of like permuting the positions of the truth table. And those of you who are familiar, that construction is exactly what's called a one-time truth table. Okay, and this is the correlation that's used in, for example, tiny tables. So this is one specific instance of FSS. How about low-degree polynomials? Okay, also there's extensions of the above. Okay, so for low-degree polynomials, well, what's one example of a beautiful low-degree polynomial is multiplication. Suppose that I have a multiplication gate. It's got 2 inputs, okay? And so what is the offset function here? I would take the first input minus some mask times the second input minus some other secret mask. Okay, and if you evaluate this out, this gives you some function of the public values, okay, and it gives you certain coefficients. These coefficients R1, R2, and R1, R2, okay, where R1 and R2 were some random masks. Remember that if I give you FSS shares of the coefficient, sorry, if I give you additive shares of the coefficients, that actually gives you FSS of this corresponding offset function. Okay, and the punchline is that these are exactly Beaver multiplication triples. Okay, so if you've seen multiplication triples, what is that? You've got some random ring element A, some random ring element B, and their product. You end up getting secret shares across two parties of those things. That's exactly the same thing as the FSS for this function class. Okay, and finally, even another thing that goes a little bit beyond some of the listed examples, but for example, already just applying the simple class of FSS gives you things like degree D gates for relatively low D, that you can expand this out as a bigger polynomial and secret share the polynomial coefficients. Gives you more general things like bilinear maps over different ring structures and so forth. Okay, so the bottom line of this slide, at least, is just kind of the observation that even using simple FSS schemes already gives you some interesting gates. Okay, but we are not done because some of the cool things that I focused the last entire hour on were these FSS constructions that are not information theoretic, but actually build on computational assumptions, but give you lightweight constructions. Okay, so just to recap, what do we know here, or some examples? For example, point functions, where the key size, as we saw here, oh, I didn't describe this actually. I got caught in a sneak here. So this plus log size of G is if you want to convert, if your output space is actually not bits, which is the construction that I described in the previous hour. But if you want to switch over to a different output group, you can do that with basically one structured correction word at the final level that's of a slightly different structure. So this is going to push you from bits to some G element. Okay. And gen and eval we saw is still roughly n pure G evaluations. Okay, these special intervals, these are exactly the distributed comparison functions. And the cost is less than or equal to, say, point function times 2. Okay, and general intervals, these are the sum of 2 of these special intervals. So each of these came up in the previous hour. And kind of just graphically, this is what they look like. So special intervals are things that are one-sided. I described how to do less than alpha. Essentially, equivalently, you can do greater than. There's not really anything tricky there. Okay, so these are 3 classes where we have lightweight FSS constructions. And what does this mean in terms of the 2PC with preprocessing? Okay, and really the question is asking, what are the sorts of gates that we can support, such that if I take that gate functionality and look at its corresponding input offset function class, that's supported by the corresponding class of the FSS functions. Okay, I wish I could give these as exercises as well. These are, I'll leave the proving as an exercise, but for example, suppose that I have a gate that has as input some group, whatever group, okay, and the output is a bit. And so this is a very, very nonlinear function, okay? This is a very high degree, which outputs whether the input value is 0. Okay, so if it's 0, then it outputs 1. If it's any other element in G, then it outputs 0. So what is this? This without an offset looks exactly like, yes, 0 is the special point. This is a 1. Everywhere else is 0. Okay, it's not a coincidence. I've aligned this with the point functions. In fact, when you consider the offset function family of this gate, what does it mean? So I take my input and I want to subtract some R, and I ask, is the input subtracted by r equal to 0, that's equivalent to saying, is this input equal to the secret value r? And this, my friends, is exactly a point function. Continuing forward, so these one-sided intervals give you things like, what is the sign of an integer value? Is it positive or is it negative? This, for example, is if I'm considering representations of Zn centered around 0. Very similarly, if I have two inputs and I want to compare, that you can basically take the inputs, subtract them, and then do a sign function on that. And again, so this one takes a little bit more maneuvering, but effectively what you're doing is you're taking a fixed public interval of sign. So this is like, I want to be, if I'm above 0, this should evaluate to 1, otherwise it shouldn't. And it's taking that and it's shifting around by some random secret offset. And this is exactly what you're hiding with these special intervals. Okay, continuing a little bit forward, even these more general intervals allow you to do things like splines. Okay, so what is a spline? This represents a graph of a gate. Okay, which splits the input space into different parts, and then each input chunk of the input has some polynomial evaluated on it. Okay, so those of you who are familiar, one example of such a thing is the ReLU function. This sort of looks like 0 and then x. And splines, and in particular ReLU, have a lot of interesting applications, for example, for approximating different types of functions, like trigonometric type functions or fixed point arithmetic sorts of operations. ReLU, for example, appears very commonly as a threshold function for neural networks. So there's a lot of interesting directions here about trying to see where this can lead and how to get this more efficient. Okay, so this is what I want to say about this first application of 2PC with preprocessing using FSS gates. And let me stop and see if there are any questions about this part.
Yes, there was one question, and this is if we can reuse the same FFS gates for multiple inputs during the online phase, where I think inputs relies here to like circuit gates.
Unfortunately not, and I'll explain why. So each of these FSS shares that I'm giving you are tied to some like random secret mask. And effectively, if you were to use the same FSS shares for two different parts of the circuit, okay, let me think about this. Okay, at least the simple version is no. Maybe there's some sort of optimization. I would need to think more about it. But at least the initial thing is that you can't directly reuse it, because as soon as that would basically require that you publish two different versions with respect to the same mask that are masked by the same value in order to use the FSS, which is tied to a fixed sort of mask offset. I'm not sure if that made sense, but that would certainly be a problem because if I see two different values that are masked by the same secret mask, I see correlations between them. It's like using a one-time pad more than once. So what does it mean? That means that ultimately, if you have some circuit with a bunch of gates, at least how we know how to do things right now, the preprocessing material will require one set of FSS keys for each gate. And that's a really interesting direction to try to improve and in fact see if you can piggyback somehow for multiple instances of the same gate, or for example, if you could somehow generate these keys in some way, like a pseudorandom correlation generator for FSS keys. I'll leave that for when you guys see what pseudorandom correlation generators are.
Okay, thanks. I think this is all questions for now.
Great. Okay, in that case, let me totally diverge. There's some word I'm searching for there, and just tell you about some random cool things about FSS. So certainly feel free to jump in if there are questions. I have kind of a few different slides, and then I'll say a little bit about other connections and then close things up with open questions. So one thing, which is something actually that a few of us has been looking into recently. So this is a joint work that's still a manuscript together with Niv and Yuval and a student of Yuval's, Victor Koborov, looking into what we call a programmable DPF. Okay, so recall that the DPF key construction that we have, it's relatively tight, it's great. And I really don't know if I can shrink it anymore. I would really love to be able to do so. But one thing that you could potentially hope to do is at least to shrink it so that one of the two keys is very small. Okay, I've added this gray thing because the final construction is not going to have the same structure, and maybe actually the second key will be a little bit bigger. But the ultimate question is can you somehow make it so one of the keys is very small, but the second one is still sublinear? Otherwise, you can do, for example, just like kind of trivial approaches where one is just a PRF seed and the other one is just like the truth table XOR. Okay, so this is the goal, and we play around with this, and we find that there's some interesting applications, and we are indeed actually able to construct such an object, building very closely on something called a punctuable pseudorandom set. So this is a notion that was put forth by Henry and Dima, Corgan Gibbs and Kogan, in their work on online-offline private information retrieval. So in that work, they get something that's almost a DPF, or rather in the sense that it's they get two-server private information retrieval, and it has a very similar flavor, like you kind of might imagine here, where one of the servers goes offline. So you can kind of think about, for example, with Programmable Dpf, I give one of the servers the short key, and then I don't really need to talk to him again, as long as he knows regularly, okay, at these time checks, I need to give some FSS output, and it can go from there. So this online-offline private information retrieval gives a scheme for private information retrieval, as you might guess, that has this kind of flavor. But the reconstruction effectively is something more complex. Okay, see, just a second. Let me change my audio issue here. Can you hear me?
You're very low in volume.
I'm very low. Was I less low before? We're good? Okay, thanks. Great. Anyway, so what they achieve is almost there, but it's not quite a DPF in that it doesn't have this sort of additive or linear reconstruction. And so we show that there is a way, actually, you can push it and you can get all the way to a DPF. And one of the things I think is very interesting, that the construction in this work is very different from the DPF construction that I showed you in the previous hour. So just kind of roughly, for example, the construction on one side or the other is going to be some kind of punctured histogram. So loosely speaking, each of the parties is going to have a bunch of pseudo-random evaluations. Each of these evaluations is going to be like a ball being tossed into some collection of buckets, okay? And you'll build this so that one of the parties is missing one ball, and that's going to be exactly missing a ball in the bucket that you want to have the non-zero value for your DPF. And it turns out you can do that relatively simply. So this is directly going from like these puncturable pseudorandom sets. For those who are familiar, for example, I can just take a PRF and give you a punctured PRF that punctures at one of these like ball values if the random outputs is like throwing a ball. But this is not secure. Okay, it's almost secure. It's 1 over polynomial secure. For example, if I see a punctured histogram, I have a bunch of random balls in buckets, and now one of them I've removed a ball from, this is actually changing the distribution in a way that is 1 over polynomial observable. Okay, so for example, if I have one bucket that's lower than the others, it's very likely, or it's more likely at least, that's the bucket that I removed a ball from. Okay, so this kind of direct thing gives you this 1 over polynomial version of a programmable DPF. And we also show that there's a way that you can convert this of amplifying in order to get negligible probability of error. So yeah, there's a lot of different trade-offs there. very different structure. For example, the cost of a single evaluation in this scheme ends up being the same, unfortunately, as the cost of a eval all. But I think that this is a really interesting direction to follow up on, partly just because it is so different that, for example, we're getting a little bit stuck in the previous approach, this tree-based approach. So I think it's very interesting to try to explore different directions there. As I said, I'm going to be just kind of highlighting a little bit of different things. This whole presentation, I've been keeping to the case where you're splitting your function into two shares, and one of the two shares is sort of corrupt, or that is that I'm considering the view of somebody who sees one of the two function shares. Okay, but you can consider, for sure, cases where there's more than two different parties. And in particular, you can consider either just security still against one, like privacy against one of these shares, or against some t that's greater than one. And let me say, so if you increase the number of parties, but you don't increase the security threshold t, then actually your life becomes easier, okay? So all of the constructions that we have carry over to those cases. For example, you can even just ignore one of the servers. But there's interesting questions there about, first of all, trying to get better constructions. For example, if you have one corruption and three different parties, maybe you can do something better there. And we don't really know. For this slide, I'm addressing the question, the elephant in the room. So suppose that you want security against more than one. And the bottom line here is that what we have sort of sucks. And you can, I suppose you can quote me on that. Maybe you shouldn't, but so to give you an idea, for example, if you look at the case of where we had two parties and t equals 1. So actually this quote, this is the BGI 16. This is what we saw before. So with one corruption, we can get like n times lambda. As soon as you go even just to 3 parties and 2 corruptions, this beautiful n turns out into this disgusting 2 to the n over 2. And let me remind you, so 2 to the n is like the trivial truth table secret sharing construction. So the savings here are like, instead of doing the entire truth table, you only need to do sort of square root of that, but that's pretty bad. And in fact, I'm not helping my case here, my advertising, but it even gets a bit worse. So suppose that you have n parties and you want security against n minus 1 of them. Our current best solution not only has this 2 to the n over 2, but actually also an exponential term in the number of parties. So let me leave this not as a negative, but rather this intriguing direction for future research. And unfortunately, mentioning though that this is not an easy question, or it seems like it's going to take certainly new ideas. And there's a really actually intuitive reason. Why is it the case that security against one party has a qualitatively totally different structure in terms of what the keys look like? And just to give you a flavor of this, so for example, suppose I've got 2 parties and I'm secret sharing a 0 between them. Okay, for example, like DPF, we want to secret share 0. If I have 2 parties with security against 1, that means that secret shares of 0 are identical values. So I know exactly what they're looking like. And for example, if I tell person number 1 to do some function on his share and person number 2 to do the same function on his share, that's going to be maintained, that we keep the same share, which means that we remain secret shares of 0. As soon as you go, for example, to 3 parties with 2 corruptions, even kind of loosely thinking about the secret share value. So say that the 3 of us now have some 0 secret shared across us. But in order to have security against 2, that already means that, for example, say I want an additive sharing across the 3 of us, that there's so many degrees of freedom here that whatever I have, well, I only know that what you 2 add up to is equal to this, but sort of how that is distributed across the 2 of you, I don't know. In fact, it's important that it's crucial that I don't know. And this turns out to make things really much more complicated for trying to get correctness of getting these kinds of homomorphisms or function secret sharing schemes. And I should mention that this limitation carries up not only into this category of sort of lightweight constructions from one-way functions, but trickles all the way through the, this beautiful sky and mountain and valleys of constructions that we have. That in many cases, what we can get for two parties is much, much better than for 3 parties. But I should say, so there are some interesting things that can be done. So in fact, there's a recent work of, I think it's Ban, Kushelevitz, and Ostrovsky, for example, that showed that you can get some improvements if there's a gap between the number of parties and the number of corruptions. And this is leveraging some kind of NPC type techniques, where if you have this gap, you can kind of do like multiplication type structures, but a bit more interesting than that. And as an example there, so say for instance, you have 5 parties and 2 corruptions. So this is not in m-1, but there's a bit of a gap there. Then for example, they get key size that scales as 2 to the n over 4 instead of 2 to the n over 2. So still a little big, I would say, but some interesting progress there. Big, shifting around, sort of taking a turn about different topics here. Another thing I wanted to mention is some things that we know about how does function secret sharing relate to other cryptographic primitives and cryptographic objects. So I alluded to this much earlier, but in fact, we know for sure that certain forms of non-trivial FSS, which I'm not going to define, but in particular includes things like even just for point functions or for intervals, a lot of simple classes like this, that this necessitates existence of one-way functions. And even a little bit further than that, so we were able to show that if you look at the share functions, these function shares, so F0 and F1 on their own, that each one of those is and must be a pseudorandom function. And sort of the intuition there is that if I have one of these functions, right? And the question is, if I could sort of predict some of the outputs of your function in different values, that would give me some bias, that would give me some information combined with what I have about what the function output would be at certain inputs. And roughly speaking, if your function is such that you should not know such information, then that must mean that you cannot get any sort of useful prediction about your opponent's or the other guy's share value. This bullet looks very contrived, okay? Let me explain this. I like this bullet a lot, and I will also explain why. If you have function secret sharing for some class of functions, okay, that contains the decryption circuit class for some symmetric encryption scheme, okay, then this implies some object that seems hard to get, okay? Specifically, it's some, okay, amortized, never mind that, but it gives you some sort of succinct communication secure computation protocol. Okay, this, in fact, I almost included the slide from Eurocrypt 2015, which is ancient news right now at this point, where I put this like big red section. This is a big barrier. This means that probably we cannot get FSS or comparable objects from things that don't already imply, for example, fully homomorphic encryption. And I said I like this bullet a lot because we actually did something a little bit surprising to us, at least, which was that we were able to build FSS for a class of circuits that include these decryption circuits, namely the class of branching programs, or Nc1, from the decisional Diffie-Hellman assumption. And what this meant was that actually for the first time, we could get something that we only knew how to do from basically fully homomorphic encryption, which we only knew how to build from lattices, or LWE. It was the first time that we could get something comparable from these new mathematical structures like DDH and discrete log type assumptions. So I'm putting that out there, not so much as like, oh, this is a hard barrier, but rather maybe this is a barrier, or maybe this is an interesting opportunity. Another object, so something called a private lead puncturable Prf. Okay, so a punctured PRF without this privacy roughly is a pseudorandom function where given a master key that allows you to evaluate the pseudorandom function on any values, you can generate kind of a handicapped key that punctures out one input. Okay, so I can give you a punctured key which lets you evaluate the pseudorandom function on all inputs except for some special XSTAR. Okay, a privately puncturable PRF is one where when I give you this punctured handicapped key, not only does it have the right correctness properties, but also you do not know which is the point that was punctured. So the privacy here is about the punctured point. Okay, maybe this already sounds a little connected. And in fact, this notion of this object of privately puncturable PRFs imply DPFs, and they imply even a stronger version with some sort of adaptive property. In the sense that, for example, if I take the master key to this PRF, that will be one of my DPF shares, and that is independent of the point that I want to puncture. Sorry, the point that the DPF point, the special point alpha. Okay. Then once I learn what alpha is, I can actually at that point generate the second share, which is like the privately puncturable PRF, which is punctured at the point the special input alpha. Okay, and you can kind of it takes a little bit of work that gives you a random value instead of exactly 1 at that point, but that's that can be handled. And actually, another aside here, so this structure seems to already give a construction of DPF where one key is very short and the other one is some kind of punctured key, which I mentioned was like a goal of this programmable DPF. And indeed, this does give such a thing. The goal of the programmable DPF construction, the slide that I mentioned, was to do this using just one-way functions and light cryptographic techniques. So privately puncturable PRFs exist. There are various constructions of it, but all of them use a public key assumption. So things like LWE, for example. So the last bullet on this page, at least, is a new one that I just recently learned about, something called targeted lossy functions. So this one's really out there, but if you guys have heard of lossy trapdoor functions, this is some sort of weaker variant. It was recently put forth by Willie Quash, Daniel Wicks, and Brent Waters. And sort of weaker in the sense that there's like only, okay, never mind, I'm not going to define what any of these things are, but I will give you the pointer. And it turns out, so I was in the talk of Daniel the other day, and he was telling me about, well, telling everybody in the talk, including myself, about what are these things, how are they useful, what are the constructions, and then at the very end he said, oh, and by the way, we found out afterward they're equivalent to DPFs. And this was a twist I was not expecting, and I think it's very interesting. So they end up giving a construction of something, and kind of in retrospect, the construction does look very similar in flavor to our DPF construction, the tree-based thing. And apparently the two notions are equivalent, and it actually seems like an interesting point of looking forth into to see if there's anything beyond that can be said. Another thing that I want to mention, and I'm starting to kind of close up a little bit here, is that, so I've talked about FSS as having potential maybe for applications, for example, private querying to databases, private writing, and so forth. And I want to put a little bit of facts behind my words here, that there have been some, at this point, an assortment of systems that have been built on top of function secret sharing, or I've used that as an important tool. And I want to call out some of them and then list some of the other ones. So this one here, Riposte, this is back in 2015. This is a way of using function secret sharing to get anonymous broadcasting. And very loosely, what they do is they take exactly the structure of this private histogram incrementing type of thing. So think about that there's this big list of slots, okay? And it starts that all the slots are empty. So these slots, the message values are held secret shared across 2 different servers, okay? And now to broadcast a value anonymously, a client comes along and chooses a random slot in which to write his message. Okay, and this is implemented by taking a DPF where the payload is equal to the message, and the secret input, like the special input, is just a random number from the slots. Okay, so one client basically now has a secret sharing of his message in, say, slot number 5. Another client comes, chooses another random slot, secret shares his message. Many people come along. Okay, then after many messages have been placed, then the servers can take their secret shared data, like secret shared values, and bring them together. What everybody learns now is just kind of the union of what were all of the messages, but the connection between which message came from which client is broken. That's protected because of the privacy of the DPF. Okay, and they showed how they built the system with actually millions of users and so forth. A Splinter. So this is a system that implemented some of these private queries. So it was effectively some sort of private Yelp clone. For those who know, this is for ratings for restaurants in the US, flight search and map routing. The queries that they implemented were kind of an interesting range of things. So match, range queries, max min, top K, with relatively efficient latencies. For example, the Yelp-like thing had 40 different cities worth of restaurants and New York City traffic map, which is pretty legitimate. And something that's kind of interesting here is that they actually built so they were able to kind of modify, and they had the servers do some local computations that allowed them to support queries even a little bit beyond what classes of functions we have FSS for. So this is a nice another position where there's some kind of building that can be done there. I mentioned this one also briefly before. So this is like the DPF competition to ORAM. Actually, I like ORAM a lot as well. This is Oblivious RAM, which Gilad is going to be talking about. But in this work, 2017 CCS paper of Dorner and Shalat, they showed a kind of surprising result, which is that in the case of two-party secure computation, okay, where the program that you want to execute is not a circuit, actually, but it's expressed as a RAM program. Okay, so this is very motivated to be able to support 2PC of these kinds of programs directly without needing to take the RAM program and unroll it to this gigantic circuit. And the standard sort of approach for doing this is that you have is an additional layer, because you need to protect where say you have like some public database or even secret shared information across the two different parties. And one of the things that you need to do is make sure that where you're looking at positions of this memory tape or database are not revealing information about the values that you're interested in or the values that are actually written there. And this layer is typically done by putting a layer of oblivious RAM, and you'll see more about that in a future lecture. But it turns out that even though oblivious RAM, as I said, has relatively much lower asymptotic cost for the lookups. Okay, so for example, if I want to actually look up some item, there's some overhead of additional items that I need to look up in order to maintain security. And ORAM only requires you to look at something like log the database size, many additional entries. Okay, versus something like a private information retrieval. Here I can view this as like never mind how, but in general, private information retrieval requires you to touch everything, every single one of the database items, and do some computation to compress down. And at first glance, that looks ridiculous. Okay, obviously the log overhead is going to be much better than the linear overhead. And what they ended up showing is that because the actual decision of which are the log positions that you're going to look at, that's something that needs to be kept secret. So that needs to be emulated via a small-scale secure computation. That procedure of deciding is much more complicated for oblivious RAM schemes that we have than it is for private information retrieval based on this DPF schemes, which are relatively simple, like these generation procedures of splitting the function. And what that ended up being is that despite the huge gap in the wrong direction for the asymptotic complexity, that concretely, when you're doing this secure two-party computation, it's actually much better to use DPF-based private information retrieval instead of oblivious RAM. So for example, as long as your database is not too big, where at some point the asymptotics will take over, but they showed, for example, if your database is less than around 2 to the 30 entries, then you can get a lot, actually a surprising amount of improvement in things like the time and the memory and the initialization costs of these schemes. In fact, I should mention this paper, this Dorner Shalat, CCS 2017, was the best paper of CCS that year. Okay, so I'm not going to go through the rest of them in great detail. I actually even discovered a few new ones while making these slides. But what I want to convey here is that there's a lot of interesting use cases, that there's a lot of potential. There's even more different cases. Just to sort of highlight, for example, where are DPFs or other forms of FSS being used? So for example, private set intersection, Benny will talk about that later on maybe not about this topic, but he will talk about private set intersection later in this school. Private contact tracing, encrypted search systems with distributed trust. Poplar is a work actually I'm joined on with co-authors. I think Henry will be talking about this later, right after this talk. Things with private time series database, high bandwidth anonymous broadcast, for example, the Spectrum things is a follow-up of a post looking at improvements there. Private nearest neighbor search. The bottom line is that there's a lot of really interesting directions, and for me personally, this is very exciting to see that this tool, which kind of in of itself is this, in my mind, like this very simple and kind of beautiful primitive, that it can have potential applications to the real world and in all sorts of different domains. Okay, so I've done my mini rambling of this section, and I want to summarize and conclude with some open problems. So first of all, what did we see together? Okay, so we had these 3-hour talks. In the first talk, remember, we talked about what is the definition of function secret sharing, and this class of applications to two-server private database queries and updates. Okay, so as an example, a special case of this is two-server private information retrieval. But for different types of FSS, and in fact, even still for DPFs, you can push this much broader than just like index I is the item that I want to read or that I want to increment, for example. And there's all sorts of different things that you can do there. And like a high-level version of what are the FSS schemes that we have? Well, in general, there's this trade-off between richness versus complexity. So the richness of the function class that you can support versus the complexity of the type of cryptographic machinery that you need and the overall efficiency that we can get. So these our talk was focused on this class of different types of simple functions, things like point functions, like distributed comparison functions, and so forth. These are things that you can get lightweight constructions from any pseudorandom generator. Moving even up, there's these Nc1 constructions. I would say that these are kind of getting reasonable, but they do use public key cryptography. So if you have some instance where you want to or you need to support a richer function class, this can be feasible, but it's still much more expensive. And above, like you can get everything, it sort of follows from forms of fully homomorphic encryption, but that's a bit less interesting. In the second part, we went over constructions in detail of the distributed point function and useful properties, and also this add-on for distributed comparison function. And sort of briefly discussed a little bit about FSS for decision trees, which allows you to extend a bit further. And in this final part, so I mostly was focusing on this application of using FSS in order to get constructions of 2PC with preprocessing for different types of circuit gates. And other highlights, so for example, this notion of programmable Dpf, where one of the keys is very small and kind of be, choose your bits and then put them to the side. multi-party DPF where you have more than one corruption, and a little bit about the intuition. Why is this challenging, and what is the state of the art there? In relation to other different primitives, in addition to places where there are FSS schemes in practice and implementation. Okay, as I mentioned, I want to close up with a few open questions, some of the things that we don't know. And I would love to get answers to some of these questions. So roughly speaking, I've put it in a few categories. So for example, suppose you stick with one-way functions, trying to get richer classes of functions. So for example, can you go beyond DPF and DCF? Can you do something like certain types of formulas, CNF formulas, DNF formulas, maybe? This barrier, this was the bullet that I said I liked a lot, where if you have a FSS for a function class that includes the decryption circuit for a symmetric key encryption scheme that implies something tricky, well, in particular, that kicks in, for example, around if you have FSS for the class AC0 or higher, that basically for AC0 or higher or more complex, there's sort of reasonable assumptions that give you symmetric key encryption whose decryption circuit is in that corresponding circuit class starting around AC0. But for example, there's this gap in between, and already I should learn that at this point, the pseudo barrier might not actually be a barrier after all. It might just be an exciting new way of getting succinct, secure computation from different assumptions. Moving forward, so these multi-key things with multiple parties, 3-server FSS with security against 2 servers. Even in this case, the beat, the key that you need to beat is really not so great. This lambda times 2 to the n over 2 versus roughly lambda times n. For both of these things, trying to show lower bounds or further barriers, these are also interesting directions. For the FSS constructions that we have, trying to see, can you push the efficiency anymore? And this is really motivated. I mentioned this before. For example, suppose that you can even cut the key size of DPF by a factor of 2. I would be fascinated by that. And this would already give you a ×2 savings in a range of applications. On the other hand, can you potentially prove some sort of lower bound or barrier that you actually need something like this? And this is not clear. So upfront, for sure, you need at least lambda bits for security, and you need at least n bits, even just to describe the function that you're trying to secret share. But there's no reason why you need lambda times n as opposed to something like lambda plus n. So I described the construction for a single point function. Turns out, and you'll see this in the pseudorandom correlation generators section, turns out there's actually a lot of motivation for trying to do FSS for what we call multi-point functions. So instead of having all zeros in a single one, there's like a sprinkling, a few ones. Maybe there's 20 ones. So you can always do that by taking 20 totally independent copies of DPFs and sort of just adding them together. And you can do a little bit of savings by kind of piggybacking on common tree structures. But it really gives you something that's only comparable to something like 20 times overhead. And so we sort of have solutions. You can put some stronger machinery onto it, and you can get some savings. Things like batch code and cuckoo hashing, if you guys are familiar with these things. If not, then never mind. But there's a lot of motivation, in particular, for even if I can't beat the DPF key size for a single DPF, I would still be very happy if I could beat like this amortized cost, that instead of 20 times the cost for 20 points, that you could do much better than that. Okay, and I didn't really talk about these mid-level constructions, these things from DDH or from Palier and so forth. There's a whole range, this could be another 3-hour talk, just talking about some of those things. So there's a lot of really interesting directions. New and improved applications. This list is growing day by day. It's really, really exciting to see. And overall, kind of just closing everything up here, I think, as I mentioned, this seems like a very natural, fundamental kind of topic And I'm just really excited to see where is this going to go and open up even new directions in the future. And so this one thing I didn't even talk about is that, you know, kind of a path. I didn't talk at all about malicious parties, really. I just teased you with 1 or 2 sentences and then told you Henry will answer your questions. But for example, even looking in that direction led us to different notions of proving on secret shared data that ends up having applications to, you know, zero knowledge compilers for multi-party computation protocols with low communication. There's a whole lot of things. This topic, I started in this topic as a fresh postdoc. Actually, I got pulled in because I had works with punctured PRFs, which ended up not really giving a direct solution. But since then, it's exploded, and it's such, you know, fantastic different directions, and it's been a really fun ride. So let's see what happens, and I hope that you guys solve these problems and you tell me about them.
Hey, thank you, Alette. It was a, you know, wonderful, you know, 3-hour lecture on this topic, and at least for me, it made many things much clearer and opened quite a few things to explore. So thanks a lot. And we're going to post this on YouTube, and I'm sure that many people will find this valuable. If people have more questions, you can post them on the Slack channel, and Alette will probably see them later. And so thank you, everyone, and we'll meet again in an hour and a half. So bon appetit for lunch or dinner or whatever, breakfast, and we'll see you again.
Okay. Hi, everyone. Thanks for joining us again for the afternoon session. So we're going to be live on YouTube as well, if you prefer to watch there. So we're going to have some exciting talks this afternoon, and starting, Henry will tell us about Prio. So Henry is an assistant professor of EE and CS at MIT. He did his PhD at Stanford with Dan Bonnet, and then he moved on to be a postdoc at EPFL. And his work has really influenced actual real-life systems. So the work the systems that he designed with his co-authors are now in iOS and Android and Firefox, and have also influenced standards, NIST standards, and the IETF standards. So as I said, today he's going to tell us about Prio, which is a system to collect aggregate statistics in a privacy-preserving way. So Henry, you're up.
Great. Thanks so much for the invitation to speak here. I'm as I mentioned to Benny, I'm like so sad I wasn't able to be there in person. So I'm hoping that that next year. I was actually so sad that I decided to make a hummus dinner last night, which was yeah. It turns out I'm a better computer scientist than I am a cook, unfortunately. But good. The other thing is I can't see any of you, so I guess, Rahul, I'm going to rely on you to channel the emotions of the audience and laugh at all of my jokes as we go. Yeah, good. So I'm, as Moore mentioned, I am going to talk a little bit about applications of some of the tools that you've seen already, but I'm going to take a pretty broad view of it. And the way I wanted to break down these two parts of the talk is, in the first part, I'll cover sort of one of the interesting challenges that comes up in practice, and that also has some kind of nice tools associated with it, which is how do you protect against misbehavior in applications of these FSS techniques that Ellett mentioned, and also kind of secret sharing protocols based on secret sharing. So the motivating application I'll talk about is private analytics, and I'll explain what that is. And then the two tools that I'll cover are is sketch verification schemes, which is kind of, you should think of it as like, how do you test properties on secret shared data? And zero knowledge proofs on secret shared data, which is kind of a more powerful tool that has a bunch of other applications. So in the first part, I'm going to give this kind of simple application, then a couple of tools. And in the second part, I'll talk about a wider array of applications. What privacy problems can we solve once we have these tools built up? And I don't know that it's going to be 1 hour and 1 hour. The first part might take a little bit more than an hour, and the second might take a little bit less. But basically, I don't care what we get through as long as everyone is learning stuff and having fun and asking questions. And I should say also that most of the work that I'll talk about, at least the new work, is with Dan Bonnet, Alette Boyle, Navigable Boy, and Yuval Shai. And then I'll mention related work as I go along. But please forgive me if I omit some. I'll do my best to cover all the citations. So good. And I guess I should say the other reason I don't usually present with a whiteboard like this, but because this is supposed to be a winter school, I thought I'd take a more a less traditional approach to doing this. So I hope it works and that you can read my messy handwriting. So good. So let me talk about one application of the tools that we'll see later today, and this has a bunch of names, sometimes called private aggregation, sometimes private analytics, sometimes, this Prio system is kind of an instantiation of this. And this is an idea that, I don't even know where to attribute it to, because it's been around for so long in so many different forms, certainly going back to say the 80s. And let me give you the problem, and then sort of the simple way to solve it, and why the simple way is not sufficient. So the kind of example application, and this is related to one of the real world applications that I've worked on, is that Mozilla, which is the company that makes the Firefox browser, web browser, wants to know something about the users of the Firefox web browser. So for example, Mozilla might want to know which web pages in the, say, Alexa top 10,000 list of web pages are popular home pages. So for example, they might want to know this because they might want to optimize the browser to work better on the popular home pages. They might want to know, demographic information about their users, what their users like and dislike. There's a bunch of reasons why they might want to answer this question. So the way this would work with sort of a non-private scheme is, let's call this non-private analytics, is that you have a bunch of users. There's say, probably tens of millions or hundreds of millions of Firefox users. And Mozilla runs some data collection service. And everyone just sends their homepage to Mozilla. So your browser phones home periodically and sends back to Mozilla what your current homepage is at the moment. So maybe this is Alice, and Alice's homepage is nytimes.com, and this is Bob, and Bob's homepage is cnn.com, and so on. So, from a privacy perspective, this is problematic because obviously, Mozilla now is a single point of privacy failure, right? So the data can get stolen in a data breach, or maybe, I don't know, what else could happen? There could be some kind of mass surveillance program that convinces Mozilla to turn over the data, or Mozilla could decide to resell it. So this is surveillance, resale, use your data in a way that you didn't want. So the basic problem here with this kind of setup, the non-private setup, is that Mozilla learns more than it needed. It, in particular, learns everyone's homepage. Right? When they just wanted this aggregate statistic, they just wanted to know which homepages are popular homepages, but instead they learned a lot more information than was strictly necessary. So the goal of these kinds of private analytics systems is to allow a company like Mozilla to compute the aggregate statistics of interest without kind of learning any individual users' private data. Yeah, because if you think about the function that Mozilla is trying to compute, they don't actually need to learn Alice or Bob's homepage to compute the statistic necessarily. Maybe with a more clever protocol, we could do this without this privacy failure. Okay, are there any questions on the setup so far? Okay, cool. Okay, so this is just one use case. And please ask questions if things are unclear. I hope that you do as we go along. So let me just mention some of the use cases for these kinds of tools. So I mentioned that Mozilla is interested in browser notification on your phone. Do you call the phone number or do you not call the phone number? That's private information, but they'd like to learn aggregate statistics about what people are doing in general. And then more recently, there's been a lot of interest from online ad companies that are trying to kind of develop more privacy-friendly ways to measure the behavior of users as they browse the internet and look at ads or not. So, yeah, and I'd say there's even more of these that I don't know about. I'm learning about as we go. So I guess one thing that I want you to take away before you even see any of the tools is that kind of this is an area in which protocol improvements can end up in use very quickly. Within a year or so, you can go from having a new idea, a new technical idea, to someone implementing it and using it in a product. So I guess this is super exciting to me as a computer scientist, as someone interested in cryptography, because this doesn't happen that often. Often it takes 30 years for something to show up in practice. And this is a place where kind of it seems like the demand for these tools really exceeds the supply. So as a student working on deciding what to work on, I hope that you think about this is an area where you could potentially have a lot of impact. So, okay, let me, are there any questions?
None so far.
Okay. At a certain point soon, I'm gonna pause and wait until there is a question because I just want to get people thinking and talking, but I'll let you think about what questions you want to ask and then come back in a minute. So, okay, here's the basic scheme. I'm going to have a basic protocol for private analytics that's sort of okay, but not good enough. So I'll explain why it's sort of okay, and then we'll talk about how to make it better. And you may have seen this. This will not be earth-shattering to many of you, but I just want to get us all on the same page. Okay, so the basic idea is that we're going to have 2 or more servers store some kind of database in secret shared form. So the first, kind of annoying thing is we're going to need now 2 or more servers. So instead of just Mozilla, we're going to have, say, a couple of data collection servers. But we can talk about how you actually instantiate this in practice, but that's kind of the important caveat. But once we have this set up, what it allows us to do is have the clients kind of write their secret data into this database without revealing where or what they're writing. And this may make you think of function secret sharing or distributed point functions, and that's exactly right. This is one of the tools we use for this. So throughout basically the rest of this this talk, I'll say that all arithmetic is in a finite field that I'll call F, and what you should think of is F as being the ints modulo some, I don't know, 80-bit prime. So if you prefer, think of everything as mod p, but just to keep the notation concise, I'm gonna write this F to indicate arithmetic mod p. Okay, so now with this setup, let me explain how the system works. So remember, the problem is we have a bunch of clients here, a bunch of web browsers. Each has a home page, and these data collection servers over here, I'm just going to write 2 servers, but in practice, there could be more than 2, server A and server B. And the servers want to know what are the popular home pages for each, for each of the Alexa top 10,000 home pages. How many clients have that as a home page? So the way this is going to work is that each of these servers holds, sort of starts out at the beginning of the day with a big vector of integers initialized to all zeros. Let me write it like this. Space. So big vector of integers initialized to all zeros. And this database is going to be secret shared in the sense that if you add up these 2 shares of the database that the servers have, you get kind of a logical database that at the beginning of the day is initialized to all zeros. So each server is holding an additive secret sharing of the kind of logical database. And each entry in this logical database is going to say, sort of the first entry is the number of clients who have, website number 1 as their homepage. And the second entry here is the number of clients that have website number 2 and number 3, and so on for all of the 10,000 Alexa top 10,000 homepages, or 10,000 web pages. Cool. So then, given this setup, the clients can send kind of secret shared database updates to write or update the state of this database without revealing anything to the servers about where their update is happening. So in particular, say this first client here has, the second homepage is his. So say this first one corresponds to, I don't know, I'll write it over here. Say this corresponds to, the New York Times being your homepage, and this one corresponds to CNN being your homepage. And this client has CNN as his homepage. So what this client will do is take this big vector, split it into 2 secret shares. So split it into two vectors that are each individually going to look random. So this is going to look like, I don't know, whatever, random numbers. And random numbers here, such that when you add up these 2 things, they're equal to the client's original vector. And then the client's going to send one of these shares to each of the 2 servers. So it'll send this share to server A and this share to server B. And what the server is going to do is just going to add the client's share into this kind of accumulator that it has running. So it's going to add, now the state after this update will be whatever it is. And the second server will do the same thing. So, And once this happens, you'll see that the kind of logical state of the database is still all zeros, except there's a 1 in the position of the kind of client's update. So if this client had a 1 in the second index in its vector, then this logical database state now has a 1 in it. And the rest of the clients can do this over the course of the rest of the day. And as each client kind of makes an update, this logical database will have, you know, I don't know, the numbers here will increase, and eventually this secret shared vector down here, logical database state, will incorporate the home pages of all the clients. So this is kind of almost all the way there. So what happens? What happens next? Kind of the last step is, let me erase this stuff. So the last step is that the servers at the end of the day basically publish the contents of their accumulators, and by adding up their two accumulators, they can reconstruct kind of the state of the database and the aggregate statistics that they wanted. So whatever it would be. So I'm going to pause for questions in 1 second, but before we do that, let me just kind of summarize what we have so far. So this simple private analytics scheme. So far. So what did this simple scheme do? So I guess the first property that I want you to observe is that the simple scheme is actually simple. Simple in the sense that it's easy to implement. Right? There was no fancy crypto happening here at all. There's no, you know, barely any crypto going on at all. It's just additions and subtractions, a very, very small number of them, and it's concretely efficient. So that's good. As long as, say, the number of websites is not too big. So I said the Alexa top 10,000, not the Alexa top billion websites. So as long as these numbers are not huge, things are okay. The second property is it's actually correct in the sense that the servers get the right answer. So the servers actually, if everyone does the right thing, so the clients do the right thing, the servers do the right thing, everybody follows the protocol, the servers get exactly the aggregate statistics that they want. So they learn exactly how many clients had CNN.com as their homepage. And the last property, which is kind of the whole point of this system, is it satisfies this useful privacy notion, which is that a malicious server, if one of the two servers is malicious, it learns nothing in a specific sense about any client's data, or the client's, in this case, the data is the client's homepage, apart from what it can infer from the statistics themselves. So what I mean in a little bit more precision is that kind of for all inputs, if we think of the client's inputs as being x1 up to xc, so there's c clients, and for all adversaries that control, say, one of the two servers, there is a simulator that's such that when you run the simulator on, and there's like public parameters of the system that I'm skipping, but basically the view of, say, one of the two servers, view of server A in this execution with client inputs x1 up to xc is looks the same as the simulator when it's given only the aggregate statistic of interest, where here this aggregate statistic would be kind of the number of clients that had each of the home pages. So already, even though we haven't really done much work, this is seems like a useful private aggregation scheme. So let me pause for questions here. Can I get one?
Yeah, there are a couple of questions.
Great.
The first one is, the goal here sounds very similar to the goal of differential privacy. So is there any performance reason or some other reason to use this approach instead of differential privacy?
Yeah, this is a fantastic question. So whenever you hear privacy, I think most of us think of differential privacy first. And the difference is a bit subtle. So I think one way to think about it is, yeah, so I guess the way I think about it, there's kind of two things you need to do when you're designing a protocol. The first is what's the privacy goal you're trying to achieve, and the second is how are you going to achieve it. So think of, you're going on a trip. First question is, where are you driving to? And the second question is, how do you build the car that gets you there, or how do you drive the car? And differential privacy is really about what's the goal, what's the privacy property that we're going to aim for. And so you can actually, whereas this kind of stuff, private aggregation stuff, is really about the mechanism by which you compute some function. So to say it again in different words, differential privacy is asking which functions are safe functions to compute, right? Because what we said here is the only thing that leaks is this statistics that we're computing, but maybe the statistics we're computing are too leaky. And differential privacy is a way to reason about that. Whereas this is just giving you a recipe for computing certain types of functions. So let me say it again slightly differently. What you can do is actually modify this type of system to provide differential privacy. In addition to this is kind of a multi-party computation type of privacy definition. If you care about differential privacy, you can layer this on top. But the two kind of concepts are really, I would say, for the most part, orthogonal. I'm not sure if that was clear, but.
Okay, another question. Is there any way to prevent from users to ruin the database by pushing wrong data into each server?
Fantastic question. Okay, so this is exactly what we're going to spend the rest of the time talking about. So maybe I'll answer that question by going on to the next chunk of material, and then we can come back for more. So cool. Okay, so these are three properties. They're all useful, but maybe they're not enough properties. So in particular, is the person asking the question points out, so one malicious client can completely corrupt the computation. Yeah, so let's see how that works, right? We have these clients here. Millions of clients, and say one of them is adversarial. So what the client was supposed to do is we have these two servers, server B, and the client was supposed to send a secret sharing of a vector that's kind of 0 everywhere except a 1 in a single location. But a client could do something malicious, like it could send a 0 everywhere except 15 in a particular location. It splits its vector into secret shares and sends one of these shares to each of the servers. The servers have this database state that they're holding. This kind of malformed request here that the client sent, it looks, by the property of the secret sharing scheme, looks fine to the servers. There's no way for the servers to tell that this kind of attack is in progress. But when the servers kind of update their database state, what's going to happen is that the logical database is going to get it incremented by 15 instead of by 1. Yeah. So one malicious client can cause kind of undue influence on the output. And in particular, it can get much worse than this, right? The client can put a million in here, or it could even put -1 million, or it could put random garbage in all of these entries, right? And basically whatever the client does here is going to show up down here. So one client can really destroy the computation. And even worse than that is if you follow through what's going on here. At the end of the day, the servers don't actually know who to blame, because the privacy of the scheme actually protects the privacy of the adversarial client as well. So in the kind of the rest of this hour, and I might actually steal a little bit from myself for the next hour, we're going to talk about how to defend against malicious clients in this type of setting. And I should be a little bit more precise, but let me put an asterisk here by saying that the real goal is to do this without paying too much. Because if you've learned about, say, multi-party computation, secure multi-party computation, or other, zero knowledge proofs, other techniques, it turns out that if you don't care about efficiency, you can do basically anything you want. But if you actually want to deploy these systems at scale, you have to care a lot about the concrete efficiency. So the tools that I'm going to talk about today are all about defending against malicious clients without paying too much for it. I'll give a couple examples of this. I guess the one thing I want to say is that once you start talking about malicious security, everything gets messy. So everything gets messy, everything gets complicated, everything gets difficult, right? So in particular, let me try to convince you that this is true. So we've already talked about kind of, I guess the security properties we're looking at here were kind of, if everyone does the right thing, then everyone gets the right answer. And the privacy property was saying if one of the servers is kind of following the protocol, but I guess I mentioned malicious here, but say semi-honest security. So one of the servers, the adversary corrupts one of the servers, but does the right thing. It doesn't learn too much information. When you're talking about malicious security, you have to answer a lot more questions, right? So are you worried about malicious clients only, or malicious clients and servers, or just servers? And how are you defining an attack? So do you care about clients? I talked about clients corrupting the output, but do you care about servers corrupting the output? Or maybe you only care about servers breaking privacy. You don't care about servers corrupting the output. Or, there's basically a bunch of different flavors of malicious security that you can look at. Today, just to keep our discussion kind of constrained, I'm going to look at, I would say, kind of the simplest one, which is the servers are doing the right thing and the client is trying to mess up the output. But in some of the papers I'll mention, there's different flavors of malicious security that pop up, and different tools are needed to address each of those. I will say that sort of usually when there's a bug in one of the things I've done, it's usually relating to malicious security. So I would say for me, at least, this is the most subtle piece of what's going on here. So, okay, maybe I'll pause here for questions again, just to see if there's anything else. No? Okay. Cool. So before I dive in, I just want to say, again, for those of you who are familiar with multi-party computation, you might be thinking, well, what is new here? You can use kind of general purpose, say, malicious secure multi-party computation to solve many of these problems. And I think the point I hope to drive home today is that in certain applications, we can get kind of efficiency gains over general purpose, say, multi-party computation by exploiting two things. So the first thing that's good to exploit is that in many of these cases, the computations we need to do are either simple or structured. And this is sort of one way you can get an advantage over general purpose tools. And the other way is that in many of these cases, the client knows the entire input. And can kind of, I should say, the client knows her entire inputs and can somehow help the servers to do something. So this is vague, but I guess in the normal setting of multi-party computation, every party knows their own input, but doesn't know anything about the other party's inputs. Whereas here, there's kind of one party that knows the entire input in question. So if we go back to this picture, yeah, so I guess I erased it. Yeah, so okay. So this client, if it weren't malicious, knows its entire input, and the servers kind of want to check something on the secret shared input. Each of the servers only has one share, but the client knows everything. And somehow we can exploit that to get efficiency gains, even if the client might be malicious. So let me give kind of what I think is the simplest example of this, of how to do this in this private analytics scheme, protect against malicious clients. It's simple, and yet it's non-trivial, and it's super useful. So this is how to protect the private analytics from malicious clients. And the goal is to ensure that each client can only, say, vote once. So one client, one vote. So each client only gets to have one homepage, and they each only get to vote once, and they can't mess up the computation apart from picking their homepage to be whatever they want it to be. So this is, there's a really nice way to do this that is from this 2016 of Elet, Niv, and Yuval. And the basic idea is to have the servers check that each client submission is well-formed before accepting it. And if not, just if not, just ignore. So if a client tries to mess up the computation, just ignore whatever the client says. So let me kind of try to say this in a little bit more detail. So the honest clients send secret sharings of a vector. So call this shares XA and XB for servers XA and servers A and B. And these are vectors of dimension n, whose sum, so XA plus XB, is an all zero vector with, say, at most 1, 1 in it. So at most, there's at most one home page in this vector. And the servers want to check this property basically without communicating too much and without messing up the client's privacy, right? So one way the servers could actually check, if you didn't care about privacy, the servers could just basically exchange their shares of these vectors, which would recover the client's private data and check that it's well formed, but that would mess up privacy. So we want to somehow execute this check without messing up privacy. So the picture, the way this is going to look, is that the client sends its shares, so this XA to one server and XB to the other server, and the servers are going to interact. So if this is server A and server B, the servers are going to interact and then either sort of accept or reject. Cool. Any questions about this so far? Any more? All right, I'll keep going then. So this is the way we can solve this is with what's called a sketch verification scheme. And the scheme, I'll describe the properties that we wanted to satisfy and then explain how we actually implement it. But the basic idea is that the servers hold additive shares of a vector, some vector x. And the sketch verification scheme is defined relative to a language, L, that's, say, a subset of the dimension n vectors in this finite field. So here, for our application, this language is going to be kind of the set of vectors with at most 1, 1. So these are kind of the valid inputs that a client could have. And the sketch verification scheme, we wanted to satisfy sort of three properties. So completeness, soundness, and some kind of privacy or honest verifiers or knowledge. So what does completeness mean? This should be familiar to you if you've seen proof systems before, but this is a slightly different setting since there's sort of two servers, two independent verifiers. So what completeness means is that if the client's input is kind of well-formed, it's in this language that we care about, then honest server should accept. If X is ill-formed, so the client sends some garbage, then honest servers reject, say with high probability. And the privacy property says that if X is well-formed, then an adversarial server executing the protocol correctly learns nothing about X, except that X is in the language. And I don't think, well, okay. So basically what the way you define this formally is to say that there's exists a simulator such that for all inputs that are in the language, the view of the adversarial server on the inputs XA and XB can be simulated without access to the input itself. So what this is saying is that if you run this protocol, the adversary only can see into the brain of one of these servers. The adversary doesn't learn anything about X, the client's input, apart from the fact that it's well formed. So cool. So that's the kind of the syntax of what we're trying to do. Let me now explain how you actually do it. So let me give this protocol, and this is this BGI 16.1. And this is for checking that some input X that's secret shared among the servers is in the language of vectors that are all 0 with at most 1, 1. And say this finite field is big enough. I don't know, big 80-bit finite field. So the way this protocol works is as follows. So what the servers do is they first agree on 2 random vectors. So the first one I'll call little r, and that's just n random field elements. And the second one I'll call big R, which is just each element of little r squared, kind of component-wise. So the servers could agree on these. In practice, they would say agree on a PRG seed and then use the seed to generate a bunch of randomness. But it doesn't really matter how the servers derive these random values. That's step one. The second thing that the servers do is they compute what I'll call test values. And what these test values are kind of a succinct sketching of this big input X that the servers are holding secret shares of. So if I'll write it like this, so we have server A over here and server B over here. And server A holds this share XA, and server B holds this share XB. What the servers are going to do is each compute 2 test values. So I'll call little t to be the inner product of XA and R. And big T will be the inner product of XA and big R. So these are just single field elements. And the same for server B. So this is XB and R. And this is XB and big R. And if you look at it, so I guess I'm using this inner product notation. If you haven't seen it, so when I say this means the sum of xi ri in f. So this is just notation for the inner product. So if you look at what's going on here, what TA, little ta, and little tb are they're just additive secret shares of the value, the inner product of the client's input and little r. And these are secret shares of the client's input and big R. And the last step, which may not be completely obvious, but it is the following. So we'll use a constant size multi-party computation protocol to check the following relation. So they're going to check that little ta plus little tb squared minus big ta big tb, that this thing is equal to 0. And I claim that if the client is honest, if x is in this language, that this check will pass. And if the client is dishonest and x is not in this language, then this check will always fail. So rather than having to do these inputs, the client's input could actually be quite big. This n could be 10,000 or 100,000 different counters that the client might be incrementing or not. And we've reduced this all using this kind of sketching technique to a constant size multi-party computation, which can be done by exchanging, I don't know, 100 bytes or so on between the servers. So before I argue that this actually does what we want, I'll just point out that the communication here is super small. So it's a sort of a constant number of field elements per server, independent of the input size n. And the computation is also super small. So it's kind of a linear number of field operations per server with no kind of hidden scary constants. And so I should say, I guess here, if accept, the servers accept if so. So any questions about the protocol before I keep going?
There's one question where someone asked that why honest verified zero knowledge is sufficient when we consider malicious party.
Yeah. So for the purposes of this talk so far, I'm thinking of the clients as being malicious and the servers as being semi-honest.
One more question I have is that what if instead of vote being 0 or 1, like vote being 1, we have vote being some value alpha? How would this just be modified?
Yeah. So good. So you're saying we want to allow votes to not just be 0, 1, but we want to allow votes to be 0, 1, 2, 3, or 4?
Yeah.
Is this what you're saying?
Yeah.
So this is a good question. Maybe I will come back to that shortly, but it's possible to do. Okay. This is a great question. Yeah. I'll come back to this in a second. That is a great one. Any others that I should address before going?
No.
Okay, cool. So with the sketch verification, the servers the malicious clients can't mess up the computation. So I don't have time to give kind of the full analysis, but let me.
Just one more question.
Yeah.
Is this protocol a specific case for distributed zero knowledge?
This is, you can think of it, so I'll talk in a second about sort of zero knowledge proofs on distributed or secret shared data, and that's much more similar. I think here the distinction, at least between sort of the normal setting that I've seen of distributed zero knowledge, is there's not really a prover here because there's no proof. So this is kind of the thing that distinguishes these sketching schemes from zero knowledge proof style systems, is that in a proof system, there has to be a proof, and here there's actually no proof. It's just sort of a lightweight computation.
Okay. Yeah.
Does it make sense?
Yeah.
Yeah, and maybe when we talk about proofs on secret shared data, the distinction will become even more crisp. So yeah, so well, okay. Let me just say explain why completeness works. So the servers are essentially testing whether the inner product of x and little r squared and the inner product of x and big R is equal to 0. So this is the test that the servers are doing. And if there's only one kind of non-zero component in this vector x, this is going to be equal to ri squared. So that, say the non-zero component is the ith one. It's going to be ri squared minus ri squared is equal to 0, and then that will be, that check will pass. It's a soundness is not that much more difficult to see. You apply kind of the Schwartz-Zippel lemma in the usual way, and this the soundness error is something like 2 over the size of the field. So I won't give the arguments here. And then the privacy against semi-honest servers, and this is important. This only holds if the servers execute the protocol correctly, is also pretty straightforward. The servers don't actually learn anything. If you see what the servers learn, it's just the output of this test, and the output of this test, if the client is honest, is always kind of 1. The output of the test is always accept. So privacy is also relatively straightforward. So I'll mention so extensions. I guess I don't have time to go into all of them, but I would say maybe the answer for this is check out this Boyle, Gabor, Ishai 2016 paper from CCS. They talk about both, if the field has a characteristic 2, the test I showed doesn't work. So there's extensions there. They also talk about different extensions when you want to sketch for different properties. So maybe the client can have a 1, a 0, or a -1 in a particular index, or like you were asking, the client can have any arbitrary value, but only at a single index. Or there's a whole variety of clever tricks that you can use to sketch for more interesting predicates. So I'll point you to that paper if you're interested. Cool. Okay, so we have, maybe 10-ish minutes. So in the remainder of the time, let's see what I want to do. Yeah, so maybe I'll wrap up sketching, and then I'll use the first part of the next hour to talk about zero-knowledge proofs on secret shared data, and then applications. So okay, so one thing that I want you to be wary of in this protocol, and when you're thinking about your own systems that you're building, are these things called selective failure attacks. And these come up all over the place. I think first in multi-party computation context, they definitely come up, as BGI 16 pointed them out in this case. But the point is that the simple sketching scheme, simple sketching, does not protect client privacy against a malicious server. Yeah, so let me explain why that is and how you can protect against it. So the attack that a malicious server can run, and this is kind of a general attack that applies. So if you're designing a system and you're trying to protect, say, against malicious parties, you should always be thinking of this type of attack. Is what the malicious server can do. Say the malicious server suspects that your homepage is cnn.com, and it wants to check that its guess is correct. So what the malicious server will do is it guesses the location of the client's non-zero entry. So this is effectively guessing which homepage the server thinks that you have. And it is sort of adds an offset to its secret share that kind of shifts the non-zero zero entry somewhere else. So let me draw a picture. So this is the client. The client has sent the server's shares of a vector, and say the clients, so this is shares are XA and XB. And if you add up these shares, they're equal to 0, 1, 0, 0, 0, 0. Yeah. So if this server is malicious, this is a server, say server A is malicious, what it can do is it can add some offset to its secret share. So now it's working with XA plus delta, and the offset it's going to add is kind of -1 and then a 1 somewhere else. So what this is going to do to the effective value of this secret share is it's going to make it, look like that. So that's happened. So this is if the guess is correct, this is what's going to happen. If the guess is incorrect, something else is going to happen. So say your home page was actually here. Now, once the server shifted the shares, it's going to look like this, something like this. So this is guess incorrect. Yeah. So the server shifts the location of the non-zero entry according to its guess, and then it just runs the rest of the protocol. The sketching scheme, honestly. Yeah, so what's going to happen is if the server's guess is correct, then the protocol will actually accept, and the server will know that it guessed correctly. It'll know that your homepage is cnn.com. If the server's guess is incorrect, then the sketching protocol will reject and is going to say, oh, but this client's input's ill-formed. And then the server will know that your homepage is not cnn.com. So, this is only one bit of leakage, but it's kind of an important bit, right? Depending on what, in many applications, one bit of leakage is enough to cause serious problems. And of course, over time, you can turn one bit of leakage into as many bits of leakage as you want. So this is, I guess, something to be careful of when you're designing these type of protocols. You need to make them simple, but then not too simple. So I'll just wrap up the hour by saying, without going into the details, so recent work, and this is at IEEE Security and Privacy with all the co-authors I mentioned on the beginning of the talk. So extends the sketching idea to provide malicious security, like security against malicious servers. I should say, maybe I'll say like to protect client privacy. And the basic idea that follows, lots of work in the malicious secure MPC world is the following. So instead of the client just sending its secret shared vector, what the client is going to do is it's going to send its secret shared vector, but then it's going to send kind of some authenticated version of it. So it's going to pick a random value, and it's going to kind of, you can think of this as macking the non-zero location of its vector with a secret MAC key. So this is kind of an information theoretic MAC. So the client sends X and then K times X for some scalar, secret scalar K that the client picks. And then the server sends, or the client sends to each of the servers now shares of X and shares of K times X. And then there's some more complicated sketching protocol that the servers run that kind of simultaneously checks that the client's input is well formed and that this MAC is computed correctly. And why is that helpful? Well, it's helpful that because if one of the servers tampers with the client's input, this MAC check will always fail, and the servers will learn no information about the client's secret value. So I'm not going to be able to go into all the details on this. I'll just say, you know, see the paper for the details. And I guess just keep in mind that you should be super careful about, you know, malicious security if you're using these types of systems. So okay, let me pause and take a couple of questions, and then we can go to the break. Any remaining ones?
So there's one question: can't a malicious server also just use incorrect values of R while when doing sketch check and thus learn whether the input comes from an arbitrary set of all websites instead of just checking for one specific one?
Yeah, that's a great question. So you could say, okay, you know, what happens here if the yeah, I'm trying to think of a succinct example of this, but you could imagine that the servers pick R, a malicious server picks R to be, you know, 00001 or something like this. Some funny value like this. It's not actually random, and then maybe you worry that there's some privacy problem that pops out at the end. So the reason why that's not a problem, okay, so first is you need to come up with some means by which the servers agree on these random vectors, and these vectors better be random. But that's actually the randomness of the vectors is actually only important for soundness, because basically each let me see the best way to say this, but basically the honest server and the malicious server are going to be computing the same function of the this client secret shared data, and tampering with the randomness here because of this check at the end. Because this check at the end is done in a kind of multi-party computation, is not going to let the servers learn anything about the client's the client's private data, apart from kind of whether it's valid or not. Not sure that was terribly convincing, but yeah, I think the thing to do is, if you actually walk through the security analysis, you'll see that kind of attack is not going to be helpful.
Okay.
Anything else?
No.
Cool. So I guess we'll come back in 15 minutes. And so I'll cover the last piece I wanted to talk about this, and then maybe take 20 minutes on that, and then spend the rest of the time on applications. Cool.
Wonderful. Thanks, Henry. So we'll go to a 15 minutes break.
Great.
Hi, everyone. Welcome back for Henry's second and final hour. So, Henry.
Great. Okay, so to pick up where we left off, I guess we talked about this motivating application. We talked about sketch verification schemes. And then in the rest of this hour, I'll talk about zero-knowledge proofs on secret shared data. And then I'll try to cover as many applications as I can. And I absolutely will not cover everything that I would like to cover, but some of the other stuff I put in the lecture notes that Benny will post online. So good. So let me tell you now what a zero-knowledge proof on secret shared data is. And how it's relevant to the applications that we've been talking about so far, and then I'll talk about other applications in a moment. So this is, you should think of this as like, sort of like these sketch verification schemes. With a proof. And who provides the proof? Well, the proof comes from the client. So the client, the servers are not only going to check some property of the input that the client has provided, but the client is going to provide some extra information that's going to help the servers check this proof. And I'll try to explain why this is interesting and why we might actually get more powerful things out of this zero-knowledge proofs on secret shared data than we can with sketching. So the picture that you should have in mind is there's a prover, where you can think of this as the client, and some verifiers that you can think of as the servers. So there's one verifier here, there's another verifier. I'm just going to draw it with two for space reasons, but there could be more. And the prover has some shares of an input. So again, say this is a dimension n vector. And each of the verifiers will have one piece of the input. So as with the analytics application, you know, verifier server A has piece XA and server B has piece XB. But the difference in kind of syntax here is that now the client is actually going to send, in addition to its input, will send the verifiers some kind of a proof. And the proof is also going to be a vector of field elements, so call it pi A and pi B. And then the verifiers will kind of chat amongst themselves, have some communication, and then either accept or reject the proof. So why this is relevant to what we were just talking about? Well, the prover's goal here is going to be convince the verifiers that in the specific case of secret shared data, that the sum of their inputs is in some language that's, I don't know, a subset of the all dimension n vectors in this field. So this could be, you know, to relate it back to what we were just talking about, this could be convincing the verifiers that the sum of their inputs is a vector of all zeros with a single one. It turns out in that case, you know, the sketch verification schemes show that you don't need a proof at all. The verifiers can just test that property directly. But in other cases, like ones I'll mention in a second, a proof is actually necessary, or it seems to be necessary. So as in, but the kind of goals here are quite similar. So as in sketch verification schemes, we still want these sort of the usual three properties. So completeness and soundness and some kind of privacy or zero knowledge. Again, I'll just stick to honest verifier zero knowledge. So I'll try to sketch what these mean. So completeness here is meaning that you know, for all XA and XB that whose sum is in this language, the probability when you run this protocol between the prover and the verifier A and the verifier B on these inputs XA, XB, the probability that the honest verifiers accept should be 1. And soundness is similar to sort of the usual notion of soundness for all XA and XB whose sum is not in the language. I guess, and for all provers, for all malicious provers, the probability that these honest verifiers will accept should be something small. You can think of this as, say, 1 over the size of the field, something like that. And the privacy property is very similar to what we saw for the sketch verification scheme. It's kind of like there should be a simulator such that for all inputs that are in this language, the view of one of the servers, or each of the server, so the view of server A in this protocol should look like the output of this simulator. So basically saying that each one of the servers independently learns nothing about this secret shared value X, apart from the fact that it's in the language. So, and again, this notation just means running this three-party protocol where verifier A's input is XA and verifier B's input is XB. And I guess the prover's input is both of these things. Any questions about the syntax before I go on? No? Okay.
No.
No? Great. Yeah, at this point, I've had like 8 cups of coffee this morning. So if I start going faster, tell me to slow down. It's good. So, okay, so let me give you some useful results to know about these proofs, zero-knowledge proofs on secret shared data. So the one, I guess I'll state one more formally and one less formally. So this is from this 2019 crypto paper with Alette Boyle, Dan Bonnet, Alette Boyle, me, Niv Gabor, and Yuval Shai. So this is, if you want to look at the paper, it's 2019 paper. And the theorem says that if this language that we care about, so the set of vectors that are kind of the good vectors, is computable by an arithmetic circuit over F. So this is just a circuit that uses addition and multiplication gates, say mod P, of size C. So if the language has circuits that are not too big, then there is, say, a zero-knowledge proof on secret shared data for the same language with communication cost as follows. So the prover to verifier cost, or client to server cost, is linear in the size of the circuit, and the verifier to verifier cost, or server to server cost, is constant. And these costs I'm measuring in elements of the field F. Yeah, so this is a useful thing to know. So a couple of other points. So points about this. So I guess one thing is that this is an unconditional result. So it doesn't require one-way functions. It doesn't require any kind of assumptions. This is just an information theoretic statement. And it turns out to be, for designing these protocols, is super useful because it says that whatever the client needs to prove to the servers about its input, you can do it as long as what it's proving is not too complicated in terms of circuit complexity. And I'll give one concrete example of this. But this ends up being a useful tool. What's even more useful is that if write it like this. So if the prover and verifiers can interact, and the language is simple, relatively simple, or structured. So for example, this circuit C that recognizes, that computes the language, has degree 2, so low degree. Then the cost, the communication cost, falls to something like log size of circuit field elements. So if the client needs to prove something to the servers and the thing it needs to prove about its input is relatively low degree, then it takes actually very, very little communication between the clients and the servers to do this. So the kind of interactive setting is, I described the prover as sending kind of one proof string to each server, but you could imagine the client sends a proof string and then the verifiers send a message and the client send a proof string and the verifiers send a message, and you kind of do a bunch of this kind of interaction. In that case, when your circuit is simple, you can get much, much better communication. So I'll mention this sort of sublinear proofs end up having lots of applications. I'll mention, I hope I'll have time to mention some of them, to say malicious secure multi-party computation ends up being super useful. Yeah, maybe, are there any questions about this so far?
Yeah, there is one question. If the verifiers need to interact with each other, why not just run an MPC between the verifiers to decide whether X lies in the language or not?
Great question, great question. So there's a couple of ways to answer that question. I think the easiest way to answer the question is if you look down here, if you actually ran an MPC to check this predicate, the MPC would probably have kind of linear in the circuit size amount of communication, because typically in MPC protocols, you have to communicate kind of some bits for each gate in the circuit. And here that would be C communication, whereas here we're getting log C communication. So you're getting an exponential improvement. Even up here, it ends up being useful because the sort of concrete efficiency of the protocol ends up being better. It ends up being a simpler protocol to achieve the same properties. But that's a great question. Yeah. Any other ones on in the queue?
How does this compare with ZK for NP languages?
Yeah. So where you have just one prover and one verifier. Is this?
I assume so. It wasn't mentioned.
Yeah, so I guess in the sort of traditional setting of zero-knowledge proofs, there's only one verifier, and the verifier has the whole input, and the prover is trying to convince something to the verifier. I guess the difference here is a bunch of things. So here we're interested kind of in information theoretic statements, but also where each verifier only sees part of the input that's being proved about. So normally in zero-knowledge proof, I give you a graph. You the verifier. I give the verifier a graph, and then I'm going to try to convince it that some property about this, that the graph is three-colorable or something. Whereas here, each verifier only actually would see part of the graph. So it's a very different kind of setting, and ends up being different protocols and different applications. I hope that's. But it is very, very similar in spirit, I guess. So cool. So the full result here, I won't be able to have time to prove either of these things kind of completely. But instead, I wanted to give you kind of one special case that I hope gives a flavor of the results and the techniques that end up being used, and also why these things end up being actually relatively simple. So cool. So let me try to do that. And the example I used is actually a practical example that people have implemented that's used in real systems. So the example I'll use is checking that a secret shared vector has kind of all 0, 1 elements in a big field. So we're working mod P, where P is an 80-bit prime or something, and each server has a secret sharing of a vector, and the servers want to check that each component of this vector is a secret sharing of a 0 or a 1, not a big value or a negative value or something funny like that. So as an example application, if you want something to think about, you can think about, say, I don't know, Mozilla, there's lots and lots of applications of this, but Mozilla wants to know, say, which websites in the top, Alexa top 10,000 use Flash. Adobe Flash, which was a web technology that's kind of going out the door. Why do they care about this? Well, if a lot of the top 10,000 websites are using Flash, then maybe they still have to support it for a while longer. Or if there's only a handful of websites using Flash, then they need to go talk to those people and convince them to modernize their websites. But this is kind of the question that that a browser vendor will want to know. And what a client, how that would work in this kind of private analytics setting is that the client has this vector, and each component of this vector is a 1 or a 0. So this is, something like this, where the ith component is a 1 if the ith, website, served Flash content to the client. Yeah. So valid inputs in each of these components are zeros and ones. Does this make sense? Rahul, are you good? All right, cool. So, right, so what's going to happen is the client now is going to send a proof to each of these servers, server A and server B, and the servers are going to interact and then accept or reject. And the servers are trying to check whether their shares, so XA and XB, when you add them up, are kind of this in this language. So it looks very, very, very similar is the sketch verification stuff we saw already, except with the addition of the proof strings that the client has to send. You could ask, is it necessary? Why can't we just be more clever and cook up a sketch verification scheme for this language? And it turns out that in some settings you can actually prove that there are languages that kind of require either a lot of communication between the servers to check, or some communication between the clients and a lot of communication between the clients and the servers to check. So in some settings, you can actually show that this sort of sketching alone without any interaction with the client is kind of not sufficient if you want a sublinear amount of communication between the servers. So I'm going to try to sketch the protocol that actually does this. This may be a little bit ambitious, but I hope that even if the whole thing doesn't make sense, that you get kind of a flavor of what's going on. But I would feel bad if I didn't at least try to give you some of the technical detail. So the idea here is as follows. So we're going to let the client's input, the secret shared vector, be this vector x1 up to xn. And we're going to define 3 polynomials. Over this field. And the polynomials are going to be that's for all points in, this is a set 1 to n. The first polynomial is going to satisfy f of I being equal to xi, so the ith input value. And g of I, the next polynomial, is going to be xi minus 1. And h is going to be f times g. Yep. So the first polynomial is f, the second polynomial is g, the third polynomial is h, and they have this super simple structure. So these guys, I guess, are going to have degree. If we pick the lowest degree polynomial that satisfies these constraints, is going to have something like degree n, and this guy is going to have roughly twice the degree because we're taking the product of 2 degree n polynomials, so something like degree 2n minus 1. And I'm abusing notation here only slightly in that I'm calling these points in the finite field 1 to n. So forgive me for that. Okay, so why is this kind of the right thing to do? Why is this the right idea? So what you can observe is that if x is in this language of, I'll write it up here. So this language is the kind of 0, 1 strings. If x is in this language, then for all I in 1 to n, h of I is equal to 0. So why is that? Well, h of I is equal to f of I times g of I, which is equal to xi times xi minus 1. And if x is 0 or 1, that should be 0. And the finite field. Yeah. So just testing whether x is 0 or 1. Okay, so that's first thing to notice. Second thing to notice is that if x is not in the language, then there exists some I in 1 to n, such that h of I is not equal to 0. Well, by basically exactly the same argument. So pick the I, if x is not in the language, then there's some I for which xi times xi minus 1 is not equal to 0. And then h of I can't be equal to 0. Yeah, so that's the second, basically the same argument. Okay, so this is almost all kind of the setup that we need. The last key facts that probably won't be obvious, but that are not so difficult to show, is that if the servers are given shares of x, of this input x, they can compute shares of f of r and g of r for any random points or any points in the field without communicating. And the reason for that is that if you look at how these polynomials are defined, f of r for any r that the servers pick is actually just a linear function of x. And so the servers can compute linear functions on secret shared data without communicating, and therefore they can compute shares of kind of the evaluations of these polynomials without communicating. So this requires just kind of writing down what the equations are for polynomial interpolation and evaluation and seeing that they're actually linear functions of x when the polynomials are defined like this. That's key fact number 1. And key fact number 2 is given shares of the coefficients of this polynomial h, they can compute shares of h of r, again for any r and f, any r in the field, again without communicating. And this is also just the fact that that evaluating a polynomial at a public point is just a linear function of the coefficients of the polynomial. The fact that we're using a linear secret sharing scheme is super helpful here. Any questions about this? I can't tell how much chaos is in the chat, so I'm going to rely on you to let me know. Okay. So good. Okay, so this is all seeming a bit abstract, but let me try to explain now how we use this to check the thing that we wanted to check. So let's see the recipe here, and this is a bit only lightly simplified, is as follows. So the client in this protocol computes this polynomial h and sends shares of its coefficients to the servers. So that's the proof. This is the proof. Is shares of the coefficients of this polynomial h. And this requires something like n field elements. Next is the servers check that h of I equals 0 for all I in 1 to n. So how do they do this efficiently? Well, I just, the second fact here was that if you're given shares of the coefficients of this polynomial h, they can compute shares of h evaluated at whatever point that they want. So the servers just kind of compute locally without communicating. They compute shares of h1 up to hn, and then they take a random linear combination of these and check that it's equal to 0. So this is kind of a randomized test with like one field element worth of communication that h of 1 up to h of n is 0 everywhere. Yeah, so that's the second thing that the servers do. And the third thing is they kind of need to tie their input x to the values of this polynomial h. So what the servers do then in the last step is check that f times g equals h. So remember, f and g are these polynomials that are defined by the client's input, and h is the proof that the client sent. So if f and g are kind of computed from the client's input, and h is also correctly computed as f times g, then these two facts tell us that basically if h of I is 0 everywhere, then the client's input is in the language that we care about. So the last step here, and then I'll try to kind of go back and explain why this works, is they use a randomized polynomial identity test for this. So the servers choose a random r in the field, and they check that f of r times g of r equals h of r, and this also only requires kind of a constant amount of communication by the fact that polynomial evaluation and interpolation like this can be done for the most part locally. Yeah, and this is you can do this with a constant size MPC, or you can even avoid using any kind of MPC. So yeah, so the servers accept if steps 2 and 3 accept. Yeah, so the servers are checking this thing here and this thing here. So in some sense, it's a very simple protocol. In some sense, it's maybe even if you don't have total intuition about how it works, you can be convinced that this may not actually be so difficult to implement, right? There's no hidden scary stuff going on here. I guess the idea, again, to try to give you some intuition for what's happening, is that the client is the client is giving the servers this polynomial h. The servers derive these polynomials f and g from their own inputs, and if f times g equals h, and the output of h is good in some way, then the servers are convinced that the input is in the language that they care about. So there's kind of two steps. One is checking that this h of I is equal to 0 everywhere. That's what the servers do first. And the second is that checking that h is computed correctly. And that's the last check the servers do. And if you kind of patch all of this stuff together, you can be convinced that this protocol is simultaneously complete and sound, and can be made to satisfy this honest verifier zero knowledge notion. Okay, so I felt obligated to try to give you at least some intuition for what's going on here. The thing, I'll just summarize the communication here, is the prove it verifier communication is like n field elements each. And then the verifier to verifier communication is like, I don't know, something like 4 field elements. I haven't computed this constant exactly, but it's something like 4. And I guess the other thing to see is we didn't really use any super special properties of this language here. And in fact, by kind of changing the definition of f and g, you can make this work for not only this language, but any language recognized by a circuit with n multiplication gates in it. So this is just tweaking this protocol a little bit gives you kind of the full theorem that I promised at the beginning. Okay, so the last thing I want to say about these proofs on secret shared data, which is important for the applications, but again, I'm not going to have time to prove, is that when the language is structured, or I should say, computed by a structured circuit, then we can reduce the proof size, or the prover to verifier communication. And I'm, again, not going to prove this. I would just want to tell you the basic idea. The basic idea, which sort of looks like the same idea that's used in some check protocols, if you've seen those. So the basic idea is say that the language on, I'll call it L of n, has a circuit of size n with, let me say circuit with n repeated subcircuits in it. So there's kind of some structure that's repeated n times in this in the circuit that recognizes this language. So actually, the circuit for checking 0, 1 to the n is of this form because you're doing xi times xi minus 1 a bunch of times. So what we do is we construct a zero knowledge proof on secret shared data, whose verifiers must compute a circuit so I'll call this circuit C of n. They have to compute the circuit C of n over 2 to check the proof. So basically checking the proof for the instance of size n requires computing the same circuit on an instance of size n over 2, and then you recursively use zero knowledge proof on secret shared data. So what does that mean? It means that the verifiers essentially ask the prover to convince them that the verifiers would have accepted this kind of next level check. So maybe I'll draw a picture to try to make it more clear. So we have the provers and the verifiers. So it's, I don't know, multiple verifiers here. The prover sends kind of a top level proof. And what the verifiers do is they send the randomness that they would have used to check this top level proof. And then they say to the prover, convince us that we would accept pi 1 if we checked it using randomness R1. Yep. So rather than checking the proof ourselves, we're going to ask you to convince us that we would have accepted the proof if we had checked it. And then the prover says, okay, here's the second proof. And the second proof is going to convince you that you would have accepted the first proof if you'd checked it. And then the verifiers say to the prover, okay, we're not actually going to check that proof. We're going to give you more randomness, and we're going to ask you to convince us that if we had checked the proof, we would have accepted it. And this continues, until you get to something very, very small, and then the verifiers can check that themselves. And this works when the kind of checking the proof becomes easier and easier as you go down. So kind of at each level of this recursion, we need to cut the size of the problem in half. And if your circuit has the right structure, this is possible. So, okay, I'll pause for questions in 1 second, but just to sum up, there's kind of 2 tools we've talked about for protecting against misbehavior in these kind of protocols using secret sharing. So the first one is for testing simple predicates. You can use these sketch verification schemes where there's no help from the client is needed. And if you want to test arbitrary predicates on secret shared data, you can use these zero knowledge proofs on secret shared data, which do require kind of help or a proof from the client, and but have the benefit that you can test whatever predicate you want. And the communication complexity depends on kind of how complicated of a predicate that you're talking about. So are there any questions that I should answer before I talk about applications?
There's one question. Can this be seen as a dealer-aided MPC between verifiers where the prover is acting as the dealer?
Yeah, this is a great question. So if you've seen MPC protocols, you might think of kind of a dealer as giving some inputs to the verifiers, and the verifiers are computing on the stuff from the dealer. The distinction here is that the dealer is might be dishonest, and the verifiers kind of want to compute the right thing, even if the dealer is trying to cheat them, right? Because if I'm the client in this protocol, adversarial client, I'm trying to convince you to accept my input. And so maybe I'll give to the verifiers, instead of what I should have given them, I'll give them some cooked values and hope that they'll accept my bogus input. So this is kind of the difference from the usual setting. That make sense?
Yeah. One more question. What are some interesting examples of languages with this nice structure? Yeah.
Great question. So, so one is say the one that I just was talking about. So, if you want to check that the language is kind of the language of values in 0, 1 to the n in a big field, and what the structure looks like is you have a bunch of inputs, x1, x2 to xn, and the circuit computes, multiplication of x1 with x1 minus 1, and then outputs this, and it does this a bunch of times. There's kind of a bunch of, you can think of this as like a SIMD circuit, same instruction, multiple data. And any circuit where there's kind of a repeated, I guess if you look at half of this circuit, the left half and the right half are doing exactly the same thing. And if you chop it again, you'll see that each of these quadrants is computing exactly the same function, exactly the same structure. Any circuit that has this kind of structure is amenable to this recursion. Another type of circuit is if the circuit is low degree, so particular degree 2, you can always coerce it into this form.
I think we have one more question.
Great.
Does this have any relationship with VSS schemes, because we're implicitly handling malicious dealers?
Yeah, this is a good question. I actually haven't thought about exactly what the relationship is to verifiable secret sharing schemes, but it somehow seems. I don't want to try to give an answer off the cuff, but this is a very good question. So maybe that's it?
There's a meta question, which is, can you clarify what exactly is PRIO?
Okay. Right. I was going to say PRIO is a state of mind, but this is not a very good answer to your question. No, it's so the PRIO system was, I guess, a paper in 2017 from me and Dan that had some of these ideas in it in kind of a rough form that we implemented, and that's actually what is running in Firefox and a bunch of other people have picked up, though the system has evolved over time to include many of the other ideas that I talked about today. So when people say PRIO, sometimes they're talking about this 2017 paper, sometimes they're talking about zero-knowledge proofs on secret shared data, sometimes they're talking about private aggregation, and sometimes they're talking about the artifact that kind of puts all of these things together. Good question.
We have one more question, if you have time.
Yeah, I would love to.
In PRIO, after the servers perform only linear operations to verify the proof, can we let the servers perform more general MPC between them on X without increasing the client's cost?
Yes, absolutely. So what the servers end up with is secret shares of a client's provided vector. And after this, they check the proof. They're guaranteed that the client's vector, the secret shares that they're holding, satisfy some predicate. And then they can do whatever they want with that secret shared information. So one thing that people do is you can have the servers add noise to the client's data such that it provides some kind of differential privacy. Or the servers could do a more general computation, multi-party computation on those values. It turns out, I guess I'll talk about, if I have time, one other application where something more interesting is happening at the servers. But for many of the telemetry applications, it turns out people just want to sum up private values from the client. So that's actually enough for many, many things.
Okay, I think that's it.
Great. So let me talk about applications, some other applications now. So we talked about private analytics. In the notes, I have some a couple of slides on symmetric private information retrieval, which I'm not going to talk about. What I want to do is talk about what I'll call private heavy hitters. And if I have time, which I probably won't, I'll talk about applications to malicious secure multi-party computation. So, okay. This is an example of kind of what you were just asking about, doing something more interesting with the client's data once the servers had it. So I'll call this private heavy hitters. In this, if you're interested in more information on this stuff, this is from an IEEE security and privacy paper in 2021, and the system, we called it Poplar. So recall in this kind of part one private analytics scheme, the motivating application, we're thinking of a browser vendor that wants to compute the set of popular homepages without learning any individual user's homepage. So if the set of kind of candidate pages that we're talking about is fixed, so the top 10,000, Alexa top 10,000 pages, then we already saw a way to do this. Each client sends a secret shared vector of dimension 10,000 and yeah, so on. But the problem is that if Mozilla doesn't know ahead of time which websites are kind of candidate popular websites, then the scheme that I described doesn't work. So in particular, say that say Mozilla wants to find the popular web pages. From the set of all 256-bit URLs or something, maybe even longer, say like 2,000-bit URLs. Yeah, the scheme that we sort of looked at the beginning would require each client, right? The scheme would be each client produces a vector, and this vector has a dimension 2 to the 2048, and then dot, 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 dot. So this clearly doesn't work, right? This is too much. So I want to describe kind of way for clients to do this using function secret sharing, which Alette talked about, and the malicious secure sort of protecting against malicious clients idea that I just talked about. And there's many other ways to solve this private heavy hitters problem that get sort of different kinds of privacy properties. But since we're talking about FSS and malicious security for secret sharing, I'll present one idea that uses both of these tools. So the setting again is we're going to have the clients, I guess many clients over here, and some number of servers, say 2 servers. And instead of having clients, so what we would have done before is we'd had the clients prepare a vector that's 0 everywhere, except with a 1 in the index corresponding to its the website that's its homepage. And we would have had this vector would be the size, linear in the size of the universe of of potential strings. So this would have been 2 to the 2048. So we're not going to do that now. What we're going to do instead is the following. We're going to have the clients prepare kind of a tree. So think of it like this, where the depth of this tree is n. So this is, say, all this n-bit URLs. And this tree is going to have 1 on the path to the client string. So if the client string is over here, then there's going to be 1s on the path to the client string. This client's input is, this could be the bit representation. So I guess this would be 1, 0 if it's a 2-bit string, and then 0s everywhere else. And the client's going to send secret sharings of the values on each node in this tree to the servers. So the client's going to prepare kind of two secret shared trees. such that their sum is equal to this kind of labeled tree thing, and it's going to send 1 to each of the 2 servers. So there's still a problem here in the sense if this tree has size exponential in the length of the string. So it seems like we haven't really done any work here. But the trick is to, well, there's 2 tricks. So first trick number 1, is that we can use function secret sharing or distributed point functions to compress the secret sharing at each level of the tree. Yeah. So instead of sending kind of secret shares of each value at the tree, what we can do is we can observe that if you look at the values of these nodes, there's 0 everywhere except 1 at a single location. And this is exactly what distributed point functions give you, as a way to succinctly secret share vectors of this form, exactly this form. Actually, Rahul, did Alette talk about distributed point functions this morning? This was at like 4 a.m., so I didn't see it, but okay, good. So you all are experts on distributed point functions now. So you can imagine, instead of sending these nodes explicitly, the client sends kind of keys for each one per level to each of the 2 servers. And the servers can kind of expand these keys out to get the values of the secret shares of these nodes using distributed point functions. So that's cool. So that's the kind of the first trick. And it turns out we show that if, in addition to using distributed point functions, if we just did it naively, you'd have kind of n keys, 1 per layer, and each key has size lambda n. So this would be kind of lambda n squared communication. You can do something slightly better, and actually each client only sends 1 key, and one DPF key kind of is able to succinctly represent all of the nodes in this tree. So with more cleverness, using something we call an incremental DPF, you can actually reduce the size of this compressed secret sharing to just linear in the depth of this tree. So that's the first trick. The second trick is, once the servers have these secret shared representations of these tree values, how do they find the popular strings? Because still, even though the representations of these things are compressed, the tree itself is exponential in size. So what are they going to do? So this is kind of trick number 2. Number 2, and the trick number 2 is actually not such a deep trick. The trick is just that for any string that's between 0 and n bits long, so I'll write this. The servers can efficiently compute how many clients hold strings beginning with this prefix sigma. So for any prefix, the servers can efficiently compute how many clients hold strings beginning with that prefix. And the way the servers do it is, so the servers are holding kind of these DPF keys, 1 from each client. And what the servers can do, if they want to know how many clients have strings that begin with this prefix, so I guess that begin with prefix 0, because this is the 0 index in the tree. What they can do is they can evaluate their DPF keys to get the value of this node for each of the clients. And then they publish the sum of those shares. And that will tell them how many clients have a string beginning with sigma, for any sigma. So once you do that, once you have that, the servers can actually just use breadth first search to find the popular strings. So where popular means maybe more than 1 million clients hold that string. So what the servers will do, I'll try to draw this give a picture of it. The servers will do is they'll walk down this tree from the root to the leaves, pruning all of the nodes that are unpopular. So the servers will each ask how many clients have strings that begin with the empty string. And maybe the answer is, they'll publish their shares of this value and they'll see the answer is, 37 million or something like this. So I'll say, okay, there must be a popular string, or there could be a popular string under this node. So then the servers will both look at the values of the next level nodes. And they'll say how many clients have strings that begin with 0 and how many clients have strings that begin with 1. And maybe there's only 87 clients that have strings that begin with 0, and there's 36 million something strings that begin with 1. So the servers will say, okay, there's clearly no popular string begins with 0, so we'll prune this side of the tree. We won't even explore it anymore. And we'll continue exploring this right side of the tree. And so they'll kind of walk down the tree looking for the popular strings. And you can convince yourself there cannot be too many popular strings, and thus the servers will relatively quickly be able to identify all of the popular strings by walking down the tree in this way. So I guess this is the basic idea of how you can kind of use, this is something more complicated than just computing sums over client data. The servers are actually running some kind of more complicated algorithm on the secret shared data, but still sort of relatively simple. So maybe, is there a question about this, or should I keep going?
No.
Okay, cool. So yeah, I hope. Okay, I hope if I lost you completely here, I hope the one thing that you remember is that there's this thing called an incremental DPF that lets you succinctly share kind of values on the nodes of a tree where the tree has a single non-zero path in it. So that's kind of the one primitive to remember. I want to, maybe in the remaining time, so since we're talking about protecting against malicious clients, let me say a couple of things about that in this protocol. So protecting against malicious clients. Okay, so the easy part is going to be an easy part and a not as obvious part. So the easy part is how you ensure that a client didn't send, right? The clients are sending secret sharings of values on this tree. How do we know that a client is not going to send garbage and kind of mess up the entire result? Well, the client's supposed to send, if we remember what this tree looks like. So the client's supposed to be sending secret shares of a tree that has a single non-zero path and is 0 everywhere else. And to test this, the servers can just use this same sketching stuff that we talked about in part 1, where for each layer in the tree, I guess going from top to bottom, the servers use this sketching protocol to check that each client's submission has at most a single 1. So it's all zeros except with a single 1. And this holds all the way down the tree. So if the client is being honest, it should only be sort of voting for one prefix at each level of the tree. So this is kind of the easier part is use sketch verification at each level to make sure that each client only voted once. So cool. Since we already saw sketch verification, we know how to do that. The harder part is actually quite subtle. So if we look at what happens down at the bottom levels of this tree, say this tree is actually much deeper. We have an exponentially large tree here. And at the bottom levels of this tree, the servers won't actually expand all of the nodes down here. And the reason is there's too many nodes to expand. This is an exponentially large tree. So the servers are only actually going to kind of look at the potentially popular nodes in the tree, which might be some subset. So you could worry that a malicious client, could abuse this and say send the server shares of values that are actually one in multiple places, but just not one in multiple places where the servers are looking. And this is kind of a subtle attack that lets one client get more influence than it should have had. And I guess the way that you handle this type of malicious behavior is to kind of modify the standard DPF construction to make it infeasible. So what does that mean? It means that basically, the malicious client can't cook up, 2 DPF keys such that the client knows the, 2 different places where, the key expanded values sum to 1. So in this tree that's defined by this incremental DPF, either the leaves are well formed, like there's only a single non-zero element here, or it's kind of garbage everywhere, but it can't be the case that there's kind of 2 non-zero leaves here and the client knows where they are. And there's lots I'll put asterisk here because there's kind of some details, but I guess the bottom line is there's a way to handle this, but check out the paper for the details there. So, okay, before I pause for questions, I want to mention also, one application that I would have loved to talk about that I don't have time to talk about, which is using these zero-knowledge proofs on secret shared data to get malicious security in kind of traditional MPC protocols. I have in the notes some details and pointers on that. And the basic idea is that if you have a distributed protocol where people are operating on secret shared data, you can use these proofs to have people prove to each other that they've actually executed the protocol correctly. And if you use these sublinear size zero-knowledge proofs on secret shared data, you can actually do that surprisingly efficiently with very, very little communication. So if you're interested in that, check out the notes and check out the related work I point to there. I think with that, I'll take questions if there's any left.
So one question is that can servers detect clients whose input isn't a path in a tree?
Is whose input is what?
Can servers detect clients whose input isn't a path in the tree?
Is in a path in the tree?
Isn't in a path.
Isn't in a path. Ah, good. Yeah, so you're saying like an example of that would be like this, where there's like a 1 over here and 0s over here. Something like this?
Yeah.
Yeah, where so the sketching, this kind of falls under the harder part, where the sketching will not catch that, because the sketching is only going to check that you're voting at most once. But this extractable DPF stuff, I should say the name for this is extractable DPF. Will. I guess there's some question about, whether or not this, to what extent in practice this actually matters, right? If a client is only voting once and they vote inconsistently in different parts of the tree, yeah, it kind of messes stuff up a little bit, and we can actually prevent it. But it's not so clear to me that this actually is going to cause a practical problem. But it's definitely a good question, and kind of you have to worry about these details for sure.
So one more question is that like in when you use predicates, do you leak any information regarding about the unpopular strings?
Yes, absolutely. So I didn't get into the formal security definition here is a mess, but there's a bunch of leakage because you're kind of, maybe the simplest way to think about the leakage is you're leaking all of the weights on the popular prefixes if you implement the protocol in the simplest way, which definitely leaks more than strictly the set of the most popular strings. But again, it's not super clear that how important this leakage is. And if you really wanted to defend against it, I think there's kind of more complicated protocols that you could run. I think it just turns out that, you know, when you go to implement the stuff, you're kind of trading off efficiency versus leakage, and I think it's pretty much a subjective choice at that point what you're okay with.
But a follow-up question would be like, how much like cost? How costly would it be if you don't want to leak?
Yeah, so I guess
would it be a lot or?
Yeah. So if you want to leak nothing, but the set of strings that say more than 1 million clients have, as far as I know, the only way to get that level of kind of strict security would be, I'll keep it short, but to use kind of general purpose MPC, which would be orders of magnitude more expensive.
Okay.
Okay.
Cool.
Thanks, Henry, for two great talks.
Thanks so much for inviting me.
It's really amazing to see these things, to see the behind the scenes of things that are actually being implemented and incorporated into actual systems. It's amazing to see. So thank you very much for telling us a little bit about it.
Thanks so much.
Okay, so we have a 15-minute break again, and we'll meet after that for Gilad's talk on ORAMs. Hi, everyone. Welcome to the last talk of this session. And now we're going to have Gilad Ashav, who's an assistant professor here at Bar-Ilan University. He did his PhD also here at Bar-Ilan as a student of Yehuda Linden. And then he went on to be a postdoc at Cornell Tech and IBM Research in New York. And he was also the vice president and cryptography research lead at JP Morgan. So Gilad's research focuses on secure computation, both theory and practice, on the interplay between cryptography and complexity, and on oblivious computation, which is what he's going to tell us about today and tomorrow. So specifically, he'll talk about recent advances in oblivious RAM. So we have 1 hour today and 2 tomorrow morning. So Gilad, you can start.
Thank you so much, and thank you for inviting me. I'm going to talk about oblivious computation. I have total 3 hours. Today I'm going to talk about lower bound and one technique for oblivious computation. Tomorrow we're going to focus on the other technique, which is hierarchical ORAM. Some of the slides today I took from Elaine Shi and Ilan Komorgotsky, so I want to give them the credit. Okay, so let's start. When we all studied models of computation, we talked about Turing machines and finite automata. And 2 models that are widely used in the real world are circuits and RAM, in the RAM model. In circuits, we all know we have some gates, we have wires. And if we talk about Boolean circuit, then each wire can carry a bit, and the gates could be, I don't know, AND, OR, XOR, and so on. In the RAM model, we have a CPU and a memory, and the CPU performs some operation. It can read, it can, I don't know, add to the value of 2 registers that it has, or multiply them. And then after it performs some computation, it goes to the memory and can write down something or read some information to the memory. And it provides information to the memory and reads information from the memory into his own registers. And this goes in cycles, continues for a long period of time. So we can translate a RAM program into circuits and circuits into RAM program. Emulating circuit, computation of circuit and RAM program is very easy. And the metrics are quite different also between those 2 models of computation. In circuits, we care about the size of the circuit, how many gates, how many wires, and also we care about the depth, how much parallelism we have in the circuit. When we talk about RAM program, we care about the time, how many steps we have to do, and the size of the memory, which is, we're going to denote it by capital N throughout the talks. Now, we want to look at the case where the CPU is trusted, but the memory is untrusted. Okay, so you can assume that the adversary can actually view the memory. So you can say, okay, what's the problem? Let's encrypt all the data. Whenever I'm come to write something to the memory or read something from the memory, you just use encryption and everything is good. But it turns out that there is a leakage in the form of an access pattern that it leaks a lot of information and it leaks a lot about our computation. So let's look at a few examples. What is this program? This is binary search. Okay, we have a vector of values, some starting point and start and end. I'm going to compute the middle, and then I'm going to search to the value that I'm looking for. Okay, val is the value that I'm looking for. Mem is the memory. I'm looking for some specific value, specific key in the memory. And this is a binary search that we are familiar with. And if we look at the access pattern, what we are going to access, the access pattern in binary search leaks exactly the rank of the number or the value that we are actually accessing. Okay, so the fact that I'm first going to the middle, and then if I'm going to the left-hand side or the right-hand side, this reveals information about the rank of the value that I'm accessing. if I have the following lines in my code, if I have some secret variable, and according to that secret variable, I'm either going to access some value X, some memory location X, or memory location Y. The secret variable, if I'm going to access X or Y, will actually reveal the value of that secret variable that we don't want to reveal. And this is also interesting in the case of cloud computing. So think that you have some program and you upload information to the cloud. Even though the information is encrypted, where I am accessing, what exactly the values, the locations, the memory locations that I'm accessing reveal sensitive information. Let's look at one example. Let's say that we have a doctor, medical doctor, that uploads all the genomic information of its client to the cloud. Now, suppose that the doctor always accesses regions that relate to the kidney and not, let's say, to the liver or the heart. So even though the data is encrypted, the server that sees where the client is accessing can infer that the patient has some kidney problem and not, say, a heart problem. Okay? So this brings us to introduce a new or another model of computation, which is, I'm going to call it oblivious RAM model. By oblivious, I mean that the access pattern, so this is like a RAM model, but the access pattern can be simulated. It doesn't leak any information about what the program actually accesses. Okay, so we can simulate the access pattern from the total steps that the program makes and the size of the memory. Okay, let's look at an example. So let's look at sorting. Let's look at merge sort. So merge sort of, let's look at, during merge sort, we're going to merge two sorted arrays. Let's think that the arrays are 1, 2, 3, and the other array is 4, 5, 6. Okay, so the way it's going to work, I'm going to compare 1 and 4. I'm going to see that 1 is the minimal. Then I'm going to compare 2 and 4. I'm going to write down 2. And then 3 and 4, I'm going to write down 3. And then I'm going to continue with 4, 5, and 6. On the other end, if I want to do merge of another array, which is 1, 3, and 5, and 2, 4, and 6, then I'm going to compare 1 and 2. I'm going to write down 1, increment this one. Then I'm going to compare 3 and 2. I'm going to take 2. And you see like the access pattern between those two merges is completely different. So from the access pattern, I can infer and learn what is the internal rank between the two arrays that I'm merging. So merge sort is not oblivious. On the other end, if I'm looking at bubble sort, then it doesn't matter what input I have, the bubble sort, the access pattern is the same. So let's say I'm running bubble sort on 1, 2, 3, and 4. I'm going to compare 1 and 2, leave them the same, and then 2 and 3, leave them the same. 3 and 4, I'm not going to swap anything. On the other end, if I have 4, 3, 2, and 1, I'm going to compare 4 and 3. I'm going to see that 3 is smaller. I'm going to write them down, but I'm accessing exactly the same location. So it doesn't matter what the input is, the access pattern of bubble sort is exactly the same. And you can actually simulate the access pattern. You can say, I need to write those two and then those two and so on. Okay, so bubble sort is oblivious. So now, of course, when we know that we have RAM model, we have programs in the RAM model, and we have programs in what we call oblivious RAM model, a natural question is whether we can take any program in the RAM model and convert it into a program in the oblivious RAM model. Okay, so we want to have a sort of a compiler that takes a RAM machine and converts it to an oblivious RAM machine. In terms of feasibility, okay, so the question is, of course, what is the overhead? So we have a RAM program that runs in T steps and uses memory of size n. I want to look at an oblivious RAM program that computes the same function and will take now t prime steps and maybe uses some more memory, some larger memory. So we're going to call it n prime. Now, the question is whether always we can do that, whether there is actually such a compiler. And the question is, if there is such a compiler, what is the overhead? How much we blow up our computation? Of course, there is always such a compiler. We all know that if at any time I want to access the memory, I'm just gonna scan the entire memory, gonna over the entire memory. Then it's going to blow up the computation by a factor of n. So if I have a program that runs in t steps, it's going to end up with a program that runs in t times n steps. Okay, so the question is not about feasibility. We know that it's possible to convert any program to an oblivious RAM equivalent, but the question is how to do it with minimal blow-up, or minimum overhead. So we're going to denote the overhead as t prime over t. Okay, so oblivious RAM, this notion of compiling a program and making it oblivious, it's an algorithmic technique that actually probably encrypts the access patterns. It was introduced by Goldreich and Ostrowski, and it goes back to '87. And just to write, to say it a little bit more formally, so we can look about ORAM as a machine that's in between our client and the memory. If we look at the cloud model, and the ORAM is going to receive, it's going to have the same interface as the memory. So we're going to have read and write addresses, and it's going to handle the memory for the client while interacting with the external memory and not leaking information about what the client is actually accessing. So those we're going to call them the logical addresses. This is what the program actually wants to access. And each access is going to be translated to many physical operations, many physical accesses, and does what we call the physical read-writes. Now, security will say that the physical accesses, those are independent of the logical sequence that we have over here, and we formalize it by asking for a simulator that doesn't receive the logical addresses, doesn't receive the sequence that the client actually sent, but it can produce essentially the same memory distribution accesses, physical accesses, as the ORAM that does seize the logical addresses. Okay? And of course, as always in cryptography, when we look about two distributions, we can talk about perfect simulation, where the simulator perfectly simulates the physical sequence of the ORAM. We can talk about statistical close, and we can talk about computational security. ORAM schemes are widely used. They're used in cloud computing, theoretical crypto, programming languages, databases, and then so more. Okay, I'm not gonna cover everything, of course, just showing this is everywhere. Okay, what about ORAM? Let's see some previous works. So ORAMs were introduced already in '87. And in the paper, in the work of Goldreich and Ostrowski, a framework of hierarchical ORAM was introduced that receives overhead of log cube n. And also back then, we already knew that any ORAM will require overhead of log n, where n is the size of the memory. In between, the hierarchical ORAM was improved. Those overhead was reduced to log square n. And around roughly at the same time, in 2011, there was another technique for achieving ORAM that was introduced, which is tree-based ORAM. And it also started with log cube and was reduced to log square. This time it actually achieves statistical security. And at this point of the research, there was a gap. We have two techniques. They both achieve log square n, while the best lower bound is actually log n. So there was a gap. And this gap was recently matched by two works, Panorama and Optorama. I'm going to describe tomorrow. And it's also based on the hierarchical ORAM, so it's the same technique as Goldreich and Ostrowski. It achieves log n overhead, and it matches the lower bound. And this is in the computational security. Okay, so right now we do have a gap between statistical security and the lower bound of log n. Okay, just before I actually start to talk about the technical stuff, I want to mention one more model of computation. So we looked at the RAM model and the circuit model. The circuit model is very bad if you want to access a memory. You cannot, you need to pay as the size of the memory. There's no dynamic memory access. You cannot know in compilation time. If you don't know in compilation time what exactly you want to access, you need to kind of copy the entire memory or pay something which is proportional to the size of the memory. But it's oblivious by design, and it supports very high level of parallelism. RAM model supports very nice dynamic memory accesses. You can do it in the cost of 1, but it's not oblivious, and there is no parallelism. Oblivious RAM gives you the obliviousness. And of course, you need to ask, okay, what about parallelism? So there is this notion of this model of computation that is called parallel RAM model. It also supports the dynamic memory accesses. It's not oblivious. It supports parallelism. And we can also talk about oblivious parallel RAM model and oblivious PRAM compilers that take a PRAM program and converts it to oblivious PRAM program. I'm not going to talk about this model so much. I just want to mention that there are also compilers in this direction. Oblivious PRAM compiler was introduced by Boyle, Chang, and Pass in 2016. And in a recent work at SODA, we showed that any PRAM program with T parallel time and N space, you can convert to T log n parallel time and N space. Okay. So the state of the art, as I mentioned, we have a lower bound of omega log n. There are two main techniques, tree-based ORAM and hierarchical based ORAMs. The tree-based ORAM achieve overhead of log square n. The hierarchical construction achieves log n. Okay, and what I'm going to talk today is about the lower bound and the tree-based ORAM, and tomorrow I'm going to cover the log n overhead. So before I actually start, if there are any questions?
So one question is that what is the difference between ORAM and PIR?
Yeah.
In one line, maybe.
In one line. So usually in ORAM, you have one client that is the owner of the data. We can look one interpretation. We have a client that is the owner of the data. It can move the data, can change things in the cloud, versus peer, which is maybe when I'm going and query Google, it's not my database. I cannot really move things around. I'm not the owner of the data, but you care about my query. So the difference is about the client has state in ORAM, whereas in peer, the client cannot really have states. This is why peer support many clients very easily, whereas ORAM for more than one client, it's very hard and difficult question.
Is there an overhead in space as well? If so, by how much?
So there are overheads by space. Some construction do have. Originally, the original construction blow up from n to n log n. But now we know how to do it in linear overhead, which means that it's a constant overhead, constant multiplication. Yeah. Okay, so we do it in linear.
Yeah.
Okay. So let's start. I'm going to start with the lower bound. And so the lower bound says that any ORM compiler results in a blow up of log n. By compiler, you take a RAM program and compile it to an oblivious RAM program. So the work of Goldreich and Ostrowski already showed an ORM showing that an overhead is a log n. It's based on some counting argument that I'm not going to describe. And the work of Boyle and Naor revisited that lower bound and found out that it has the following properties, which are two kind of advantages, and one is a disadvantage. So first, this lower bound is in what is called the balls and beans model. What is the balls and beans model? So if I have my memory, then I can just read or write some objects. I can read or write some balls that the program actually tried to write. I cannot take a ball and use some encoding, divide it to different cells, or do some secret sharing and so on. Okay, so I need to relate to each one of each memory block as what is so-called OPEC. It's one thing that I cannot divide. And so this is the balls and beans model. So a natural question is, maybe we can do better when we are not in the balls and beans model. And another thing that this lower bound is in the statistical security, achieves statistical security. So maybe if you assume some computational assumptions, you can actually do better than log n. On the other end, and this is what makes this lower bound very strong, is that it works already for offline ORM. What is an offline ORM? It means that the entire logical sequence is known in advance. The compiler knows exactly what are going to be all the memory, the logical sequence, including the address that I'm going to access and the actual data that I'm going to access. Okay? And even though I know all those things in advance, you can still not do better than log n over. Okay, so this is a very big advantage of this lower bound. Boyle and Naor, first of all, showed that this is the model of Goldreich and Ostrowski. They pointed it out. And in addition, they say that if you achieve a better lower bound, a smaller lower bound than log n for offline ORM that it's not in the balls and beans model, then you actually achieve an n log n lower bound for sorting circuits. And this is a very hard problem in complexity that we don't really know how to relate and what to do over there. So it's actually saying that if you can achieve a better lower bound for offline ORM that doesn't suffer from statistical security and balls and beans, you actually solve a very difficult problem in complexity. Then came Larsen and Nielsen, and they showed a lower bound of log n that doesn't work in the balls and beans model. It also works for computational security. So it's in this sense complements Goldreich and Ostrowski, and it works for online ORM and not for offline ORM. Okay, so it really complements Goldreich and Ostrowski. And what I'm going to show now, I'm going to show the ideas behind this lower. Okay, so the lower bound of Larsen and Nielsen is based on the information transfer technique of Petresco and Demain. It's in the cell probe model of Yao from 81, which says that computation is free. You only charge for probes, for actually accessing the memory. So let's look how the ideas behind this lower bound. So think that you have the logical operations that the program wants to perform. And under those logical operations, the ORM is going to translate them to some physical addresses that I'm going to access in the memory. So for simplicity, let's say that each logical operation is translated to Q physical probes in the memory. Now we are going to build a complete binary tree above those all logical operations, where the node, the leaves, are the actual logical operations. And we are going to charge some internal nodes of the physical probes that we are performing. Okay, so let's see exactly how we're going to charge. So we are going to assign each physical operation, which is going to be some read-write of some specific address in the memory, in the external memory. I'm going to assign it to this node if this node is the lower common ancestor of the two last physical accesses of that address. Let's see an example, because it's really hard to understand without an example. So let's say that those are the physical addresses that I have. So this was some read or write from the logical memory, was translated to accessing those specific location in the external memory. So I'm going to access 5, 10, 20, and 1. And let's say the 20 was visited again in this logical operation. Okay? So the least common ancestor of 20, I see the 20 appears twice. I'm going to charge 20 on this node. Okay? And let's say that the next time that we're going to ask 20 to access the physical address from 20, it's going to be in this operation. So the least common ancestor of 20 on those two accesses, it's actually the root. And for another example, 44 is being accessed also over here. So again, I'm going to charge the root for this access. Now, each physical probe that we have is going to be written at most one internal node. Note that some probes, I don't even gonna write them down, like 5 over here. If it was visited only once, I'm not gonna write it in any one of the nodes. So the total number of probes that the program actually accessed, if we count the sum of all values that we wrote on the entire tree, this is going to bound the total number of probes that we have. Okay, it is smaller than the total number of probes because some probes we don't charge in the tree. So it is enough to bound to lower bound this value. Okay, I want to now count what are the sizes that I wrote on each one of the nodes. The sizes of the sets that I wrote. So one important thing to say is that the adversary doesn't see the logical operations, but it does see the physical probes, and therefore it can also compute exactly the same tree. Okay, so you can actually see and generate this tree in his head. Now, based on the physical access pattern, the adversary can compute the tree. And for security, it means that no matter what the logical accesses we are doing, the tree, the number of elements in each one of those nodes, supposed to be the same for every logical sequence that we have. So we are going to generate, for each node, we are going to attack each node and force it to be very large. So we are going to compute we're going to generate some particular logical sequences for each one of the nodes that forces that node to be large. And because the tree is supposed to be the same, no matter what logical sequence we have, this means that once we attack that node, it's supposed to be this size no matter what logical accesses we have. Okay, so how do we attack the root? The idea is that we're going to write on this subtree, we're going to write on memory location 1, memory location 2, memory location 3, and so on, some random values, completely random values. And then on the other side, we're going to read that memory locations. Now, the idea is that this must be large because our client is small, it has a small number of registers, and we wrote a lot of information that is completely random. Because we wrote a lot of information that is random, it must be written to the memory. We cannot actually, from correctness, we cannot really just save it in our local registers. And from information transfer technique, from information compressibility, we must have written it down to the memory, and then later we must actually access those memory locations again. If we want to access this, if we want now to attack this particular node, again, we're going to have a sequence that is going to write random values over here and read those values over in the right subtree. And here we must have some, again, information that moves from this subtree to that subtree. Okay? So formally, we can write that for every node in depth D, the expected number of probes that are assigned to that particular node is n over 2 to the d. Okay, and this is essentially saying that it's the number of nodes or the number of leaves that we have in his left subtree. And the proof is by encoding or compressing argument. It's essentially saying that I cannot store this information locally. I must have written it to the external memory, and therefore later I must actually read it and learn it again. Okay, so what does it give us? So the expected number of total probes is, as we said, it's enough to sum over all vertices in the tree. So from linearity of expectation, we're going to have, this is supposed to be also greater than, sorry. This is our claim. And this is over all the nodes in our tree. Now, each node, we have 2 to the d nodes of depth d. Okay, so what we get overall n log n total number of probes. And we looked on programs that have logical sequences of length n. Okay, this was our tree. We looked at a tree that has n leaves or 2n leaves, which actually means that we must have log n overhead per operation, per logical operation in expectation. Okay, so question, I have some references over here if someone wants to look at this lower bound, other lower bounds. There are many follow-ups, some relaxations of ORAM. Maybe we don't really want to have computational distinguishability when we just want to have differential privacy between 2 programs that look the same. So even that we cannot really do better. Maybe we don't care about a compiler, we care about specific data structures. We still have a lower bound for that, and so on. So there are many papers that are already built upon of this law. So this is a good time to stop and ask ask questions.
Currently, there are no questions. Okay.
So I'm going to continue now with tree-based ORAMs. Or at least provide some high-level idea of tree-based ORAM. So those are simple constructions that actually achieve statistical security and achieve, at the end of the line, achieve log square n over. So our starting point is maybe we want to, now we are trying to build an ORM. Our starting point is, okay, let's just shuffle the memory. So I'm taking the internal memory. If instead of saying this is address 1, 2, and 3, and so on, I'm going to first shuffle everything. And what the adversary is going to see, the one who sees the memory, because everything is also encrypted, it doesn't see anything. And then when I'm accessing some element, it has no idea what I'm accessing because everything is randomly shuffled. I access something, it's completely independent of what I'm actually accessing. Okay, and then when maybe I access something else. The problem is, of course, when I come to and do repeated query, when I want to access the same element one more time, I'm starting to reveal information. Okay, so this leads us to the following design principle that blocks must be moved around the memory while we are operating on our own. So the idea of tree-based ORM is the following. So we are going to arrange the memory in a tree where each node is going to be a bucket that actually can contain more than one element, maybe log n blocks in the beginning. And let's assume for now that we also have very large CPU size. Okay, we can actually have many registers. And the idea of tree-based ORM is to have the following path invariant. So every block is going to be mapped to one random path in the tree. And the client knows it holds the position maps that tells him block X, if you're looking for block X, this is going to reside in this path, in path L. And okay, so if I want to access block X, I'm going to the position map. I see that it's on this path. I'm going to read the entire path. And so read is simple. Okay, I can read blocks very easily. Now I want to write it back. Now, maybe I want to just read it. Maybe I want to change the value. And after being read, I cannot write it to the same place because then I didn't do anything, right? And at the same time, the next time I'm going to access the same node, you'll know that I'm accessing the same value, like accessing the same address. So the block must be relocated. I'm going to write it in a different position. Now, let's say I'm going to sample a new path for that block. And I want to move the element to reside on that path. Can I write it down directly on the leaf of that path? The answer is no, because then when I want to actually read it, you will know that this is the same block as I read next time. Okay, so I cannot write it on the leaf. I can also not write it on each one of the internal nodes of the tree. The only place I can write it is actually the root of the tree. Okay, so far how read or write look like. I'm going to my position map. I'm going to see where the block resides. I'm going to write that. I'm going to read this path. I'm going to generate a new location. I'm going to generate a new sample, a new path for that block. And I'm going to write it only to the root while changing the position map and saying, now it's going to reside on the path L prime. Okay, so this is secure, very secure. All I'm accessing is just random paths along the tree. Okay, each access, I'm just accessing something random, write it to the root, and that's it. However, there is a problem. And the problem is that the root will overflow very fast. I said that each block inside each node inside the tree is, let's say, a bucket of log n elements. So after log n accesses, the root is going to explode. We'll have an overflow, and we are screwed. So the idea is to have some background procedure that evicts elements and pushes the blocks and propagate them around the tree. Okay, it's going to move the blocks around the tree to the place that they're actually supposed to go. This is going to be oblivious. We're going to do this eviction procedure obliviously. We don't want it to be too slow. If we do it too slow, we're going to have overflows. And we don't want to do it also too fast, like we don't want to write down, after one read, write down the entire tree, because this will, it's like accessing the entire memory. We don't want to do it also too fast because we want to save cost. Okay, so one idea to do this eviction is at each one of the nodes, each one of the, on each level, to choose two random buckets. See exactly, you're gonna read them back to the memory, to the CPU. See exactly on each one of these elements, there is written a path where it's supposed to go. And I'm gonna write it back into its kids, into the two children, according to the path where it's supposed to go. So if I have here an element that's supposed to go at the end of the day to this location, I will write it to its this child. And if I have someone that's supposed to go to this location, then I'll write it to this child. Okay? So at every level, I'm going to choose two random elements, two random nodes, and I'm going to push its elements downward. So everything is oblivious because I'm just choosing random nodes, touch the two children of that node, and that's it. Okay, so I don't really reveal. Everything is random. It's not really revealed, and it happens in the background. It's independent to our actually accesses that we did in the beginning of the round. Okay, so it doesn't reveal information, and it was shown that if the bucket size is log n, then there are no overflows with high probability. Okay, so each cost now is log square n. We said we are going to read the path, and each node in the path has log n blocks, so this is log square n cost. What about the position map? So we said that the client has a lot of memory, that he knows in advance, it knows internally where each element is located. So we need to get rid of that position map because it's also something that we cannot store. It's too much information on the client. So we are going to have a smaller position map. So the position map, we can group like two blocks together, and then we'll have a position map that instead of n elements, we're going to have only n over 2. Now that position map, we again can store using another ORAM on the server, and then its position map will need only n over 4 blocks. That thing we can again store with an ORAM on the server, which will need a position map which is only n over 8. Overall, we'll get log n position maps. So this is a recursive position map to actually store the position map of the tree. Okay, so overall, we got log cube n. So we got log square n from actually accessing the tree, and another log n comes from the recursion of storing the position map. So summary of tree-based ORAMs, a block is remapped to a new random path after we read it. The block must be relocated to the new path without revealing the new path. So this is when we write it down to the root of the tree. as the key challenge is to design eviction process and prove that there is no overflow. And actually, the eviction works. So general tree-based theorem worked in log cube. So again, we have 3 places where log comes from. Each path has log n nodes. Each node has a bucket of size log n, and a recursion of the position map adds us another log n. Now, path theorem, which is an improvement, reduced it to log square n. What they do is that they reduce the buckets on each node in the tree to be just a constant size. However, this means that sometimes when you try to write something, you will not really succeed. Therefore, they also have an internal stash at the client that it can store polylog n elements. Okay, let's take a look at the code of path theorem. So again, here I have a position. I'm gonna see where I'm gonna read or write A. So I'm going to the position map and see what's location. I'm gonna write a new location to that A. So I'm gonna get the uniform new value to A. And then I'm gonna read the buckets along the path. That's reading the buckets into the stash, into the internal client. I'm going to, if I want to read or write, I'm going to update the associated value of that block. And then when I see my path, I'm going to look at my internal stash, and I try to propagate as many elements as I can along that path. So what do I mean by that? Let's say that in my stash, I have an element in my internal memory. I have an element that wants to go over here, and I read this path. So when I did that, I can try to write back the element into this node. Okay, because I'm reading the entire node, the entire path, and now I see that I have element that I can write back to the tree. So I can see the intersection and put it as deep as I can towards the leaves. So this thing apparently works and can work even for buckets of size 1. Okay, so with that, I want to conclude for today. Tomorrow, we're going to describe the hierarchical ORAM scheme and see some new advances in hierarchical ORAM. And if there are any questions, I'm really happy to take.
No questions from the audience.
Okay.
Okay. So I think we'll conclude for today. Thanks, Gilad, for a great talk. And we have a lot to look forward to tomorrow, going down, from log squared to log n.
Log n.
So I'd like to take this moment to thank again all the speakers of today. And we'll see all of you tomorrow for Gilad's next 2 talks.
Thank you. Thank you so much.